One star is so old and strange that it almost broke all the rules about how stars should work. It's known as the Methuselah star, and for many years, the best estimates put its age at longer than the universe itself. That shouldn't be possible, but the statistics wouldn't stop. Everything about it, its light, its distance, and its chemical marks said I was here before I was allowed to exist. That's why we're going to talk about the star that made scientists rethink what they thought they knew about the Big Bang, life in stars, and even real time. Meet the Methuselah star. This tiny, ordinary-looking point of light has one of the weirdest cosmic resumes we have ever seen. If you go outside on a clear night and look toward the sign Libra, you will see it. A star chart only lists it as HD 140283, but scientists finally gave it a much more exciting name, the Methuselah star, after the biblical character who lived the longest. Around 179 light-years away, it's close enough that if you had a good outdoor setup, you could see the same thing that has been bothering cosmologists for years. On the surface, nothing screams record breaker. It is a little brighter than the sun, a little hotter, and not surrounded by a flashy nebula or a swarm of planets. What makes it special is not how it looks, but what its light is telling us. Methuselah is what we call a subgiant. It has already burned through the hydrogen in its core and is in the slow, graceful process of leaving the main sequence. That phase does not last forever, and its exact brightness and colour at this stage are incredibly sensitive to how long it has been alive. In other words, this is a star sitting in the perfect spot on the diagram to act like a super precise clock. The first hints that it was weird go back more than a century. Early observers noticed that this star was sliding across the sky much faster than the typical background stars. That proper motion flagged it as something belonging to the Milky Way's halo rather than the calm, rotating disk where our sun lives. Later, when astronomers split its light with spectrographs, the real bomb dropped. Methuselah is extremely metal-poor. In astronomy, metals means everything heavier than helium, and compared to the Sun, this star has only a tiny fraction of those heavy elements. That matters, because heavy elements are not part of the original recipe of the universe. Right after the Big Bang, you mostly get hydrogen and helium, with traces of a few light elements. Everything else has to be cooked inside stars and then blasted out by supernova explosions. So if you find a star that is almost pure primordial material, it means it was born very early, before countless stellar generations could pollute the gas with iron, carbon, and oxygen. Methuselah's chemistry makes it a fossil from a time when the Milky Way was still under construction. Its orbit adds another layer of drama. Methuselah does not cruise politely around the galaxy in a flat circle like the Sun. Instead, it dives in and out on a stretched, plunging path, cutting through the galactic plane and swinging far out into the halo. Orbits like that often belong to stars that did not even form in the Milky Way at all. They might be refugees from small dwarf galaxies that the Milky Way tore apart and absorbed over billions of years. So there is a real chance this local star is actually a survivor from a completely different, long-dead galaxy. Why its age is a problem. When it comes to astronomy, the age of the world is a number that feels very solid. Space projects like Planck have set that at about 13.8 billion years by looking at the cosmic microwave background, how galaxies gather, and how fast space is expanding. There are error bars, but they're not very big. That value is built into the way we talk about the Big Bang, how galaxies form, and how long things have been going on. Now drop Methuselah into that picture. To age a star, astronomers do not just guess. They model how stars of different masses and compositions evolve over time. For any given mix of hydrogen, helium, and heavier elements, there is a very specific path a star will follow on a graph of brightness versus temperature, the Hertzsprung-Russell diagram. If you know a star's temperature and true luminosity, you can ask which age track it lands on. Subgiant stars like Methuselah are especially useful because slight differences in age change their brightness and colour in noticeable ways. The catch is that you need the distance to turn how bright it looks into how bright it actually is. That is where parallax comes in. As Earth orbits the Sun, nearby stars appear to shift slightly against the distant background. Measure that wobble precisely, and you can get the distance. For Methuselah, astronomers used the fine guidance sensors on the Hubble Space Telescope to pin that parallax down with impressive accuracy. That gave them its distance, which gave them its true luminosity, which allowed them to drop it onto the evolutionary tracks. When they did, the answer that came back was around 14.5 billion years old, with an uncertainty of a few 100 million years either way. Even if you push the numbers to the youngest side of the error bar and the universe to the older side of its error bar, you are still right at the edge where the timelines barely overlap. On paper, at least in that first big analysis, this one star was trying to be older than everything. There are a lot of knobs you can turn in stellar models. How efficiently energy moves through the star, how much helium it started with, exact reaction rates in the nuclear fusion processes, how heavy elements affect opacity, and so on. Small tweaks in those inputs can move the age by hundreds of millions of years. On top of that, there are measurement uncertainties in the star's composition, especially for elements like oxygen that matter a lot for age estimates in metal-poor stars. As better data came in, especially from the Gaia mission, the situation softened. Gaia provided even more precise parallax and motion measurements, refining the distance and therefore the luminosity. New spectroscopic studies improved the estimates of Methuselah's heavy element content. Updated stellar evolution codes used those inputs to rerun the clock, and the age slid downward into the 12 to 14 billion year range, instead of sitting so confidently above 14. In most modern analyses, Methuselah is now just barely younger than the universe, not older. How we normally age date stars. It would be 1,000 times easier to study the stars if they came with birth certificates. We have to figure out their whole life stories by going backwards through the clues they've left in their light. There's also the fact that stars don't really age. Instead, they change over time. At different times during their lives, they change in size, colour, temperature, and even the way the inside is built. To find out how old a star is, we need to know why it looks the way it does now and match that to stellar evolution models, which are the only things we have to work with. The most useful tool here is the Hertzsprung-Russell diagram, which is basically the internet's favourite alignment chart, but for stars. Plot a star's brightness on one axis and its temperature on the other, and you'll find that stars don't scatter randomly. They line up in patterns, sequences, branches, and curves that represent different phases in their evolution. Stars like the Sun spend most of their lives on the main sequence, quietly burning hydrogen. Once they run out of core hydrogen, they move into new zones on the diagram that have much steeper, more time-sensitive paths. That's why subgiants like Methuselah are such clutch targets. In this stage, small differences in age make big differences in where the star sits. But before we can even drop a star onto that diagram, we need its temperature and true luminosity. Temperature is relatively easy. Its colour tells us that once corrected for things like interstellar dust. Luminosity is harder. We only see how bright a star appears from Earth, which can be wildly misleading if we don't know its distance. A star might look faint because it's tiny and dying, or because it's absolutely massive, but thousands of light years away. That's where parallax comes in. By measuring how the star shifts against the background when Earth moves around the Sun, we get its distance. With distance in hand, we can convert apparent brightness into actual power output. Then comes the chemistry. Heavy element content, what astronomers call metallicity, is a giant piece of the puzzle. Even a tiny change in the amount of iron, carbon or oxygen inside a star shifts how it burns fuel, how fast heat moves through it, and how long it spends in each evolutionary phase. So if you misjudge the metallicity, the age you get from the models will drift by hundreds of millions of years. For ancient stars like Methuselah, this becomes 10 times more sensitive because they were born when the universe had barely produced any heavy elements at all. Once all of that is measured, distance, temperature, luminosity, and metallicity, astronomers run the numbers through stellar evolution codes. These codes simulate everything happening inside a star, from nuclear fusion rates to convection currents to how light interacts with matter. For every possible age, the model predicts exactly how bright and how hot a star with those ingredients should be. By lining up Methuselah's real-world stats with the theoretical curve, you get an age. In theory it's easy. Practicing is very painfully delicate because there is doubt in every input. Error bars are in parallax. How well your tools read the range determines the temperature. Finding the metallicity of something can be wrong if some elements are harder to find than others. Worst of all, the physics inside stars, the parts we can't see, includes things like helium settling, mixing in the outer layers, and reaction rates that have tiny errors but huge effects on timescales that last billions of years. This is why Methuselah caused such a meltdown. Stars like this depend on a delicate balance between a number of different factors. If even one number is slightly off, the distance being too far, the oxygen level being too high, or the convection model being a little off, the whole age estimate changes. To keep Methuselah from being older than the universe, almost every knob had to be turned all the way to the very end of its range. And if all of your knobs are turned all the way up, the system may be trying to tell you something. The first older than the universe measurement. It wasn't because of its strange path or old makeup that the Methuselah star first made news. It was because of one science finding that seemed so strange it almost sounded like a mistake. The age estimate was about 14.5 billion years. That number didn't just make people look twice. It meant that the star was older than the universe, which was thought to be 13.8 billion years old. Scientists were aware that the measurement had some flaws, but the center number still went over a line that should never be crossed. To understand why this was such a bombshell, you have to rewind to the early 2010s. At the time, the Hubble Space Telescope was being used not just to take pretty pictures, but to do high-precision astrometry, the science of measuring stellar positions down to micro-arc-second accuracy. The Methuselah star was a prime target because its distance had always been tricky to pin down. And distance is the foundation for everything else. If its distance was off, then its true brightness was off, which meant its age was off. Hubble's fine guidance sensors were the perfect tool to make that measurement rock solid. When the team processed the data, they landed on a distance of about 190 light years, but more importantly, they had a margin of error far smaller than previous estimates. With the distance locked in, they recalculated the star's luminosity. Then they fed that value, plus its temperature and metallicity, into updated stellar evolution models. The output was shocking: 14.5 billion years, give or take roughly 800 million. That uncertainty might sound big, but the problem wasn't the spread, it was the placement. Even if you nudge Methuselah's age downward by that margin, it still sat uncomfortably close to the universe's age. And if you nudge the universe's age upward by its own uncertainties, you still barely got overlap. It was like forcing two puzzle pieces together that technically fit, but clearly aren't meant to go in that spot. The scientific community didn't panic, but there was a very real moment of, wait, is the universe wrong? Or is the star wrong? Because the math had to break somewhere. Either Methuselah had been modelled incorrectly, which would imply our understanding of low metallicity stars was flawed, or our cosmology was off, which would be a much bigger problem. At that point, the star wasn't just a curiosity. It was a ticking time bomb in the middle of astrophysics. Astronomers began digging into every possible source of error. Was the temperature measurement off due to calibration issues? Was the oxygen to iron ratio mismeasured? Did the star have more helium than expected at birth? Small variations in those values can nudge the age dramatically, and Methuselah pushed almost all of them to the extremes of what seemed physically reasonable. Then there was the universe side of the problem. Around the same time, measurements of the Hubble constant, the rate of cosmic expansion, were starting to disagree with each other. If the expansion rate was slightly different than assumed, the age of the universe could shift by hundreds of millions of years. Suddenly, Methuselah wasn't just a lonely outlier, it looked like a symptom of a bigger tension in the field. Everything was checked twice by scientists, including the paths of stars, diffusion models, parallax calibrations, and rates of nuclear reactions. Still, the star wouldn't move away from the edge of space. The wall was being leaned on so hard that everyone could feel it bend, but it wasn't breaking the universe. What metal poor really means here. Astronomers say that Methuselah was metal poor, which could mean something as simple as not having as much iron as the Sun. But that phrase doesn't do justice to what's really going on. It is one of the most chemically primitive stars still shining in the Milky Way, and Methuselah is not only metal poor, it is extremely metal poor. And that chemical mark from a long time ago could be the key to both understanding where it came from and why its age seemed impossible at first. In astronomy, every element heavier than helium counts as a metal. That includes carbon, nitrogen, oxygen, iron, and everything else created inside stars. The early universe didn't make these elements. After the Big Bang, the universe was almost pure hydrogen and helium with tiny traces of lithium. Every heavier element had to be cooked inside the first generations of stars, then scattered by supernova explosions. So when we find a star with very few of these heavy elements, we're essentially looking at something formed before the galaxy had a chance to enrich itself. Methuselah's metallicity is about 250 times lower than the Sun's, which puts it near the boundary between normal early generation stars and so-called ultra-metal-poor stars. What that tells us is simple. The gas cloud that formed Methuselah had barely been touched by previous generations of stars. Only one, or at most a few, supernovae had gone off near it. That makes Methuselah a historical artifact from the era just after the universe's first true giants died. This lack of chemicals isn't just curious, it's necessary for figuring out how old something is. Stars with less metal burn hotter and change in different ways than stars with more metal. Since there are fewer heavy elements inside the star, it is easier for energy to leave. That changes how fast the star goes from one stage of evolution to the next, how the core heats up, and how the atmosphere grows. This means that even small changes in metallicity, especially in elements like oxygen, can change how old the star is thought to be by hundreds of millions of years. In fact, early analyses of Methuselah suggested that an underestimation of oxygen abundance played a major role in pushing its age too high. Increasing the oxygen slightly lowers the age estimate because it changes how efficiently the star transports energy. This is why more recent studies, with better spectroscopy and better models, have nudged Methuselah's age into the range allowed by cosmology. There is another layer. Metal-poor stars also experience different internal mixing processes. Over billions of years, heavier elements like helium can sink toward the core, while lighter elements rise. If this gravitational settling isn't accounted for, the surface metallicity you measure might not match the original metallicity the star was born with. And if you use the wrong metallicity in models, the age estimate can drift in the wrong direction. A relic from the first generations of stars. Methuselah is not from the same generation as the Sun, or even the very first stars in the circle of the Milky Way. It comes from a much earlier time, when the universe was still healing from the Big Bang, huge stars were exploding all over the place, and galaxies were being formed by random mergers of stars. Think of the universe as being only a few 100 million years old, with new hydrogen clouds and the ashes of the first stars. This will help you understand Methuselah. Those first stars, often called population 3 stars, were massive, short-lived monsters. They lived fast, burned hot, and died violently after only a few million years. Their explosions scattered the universe's first heavy elements, seeding the gas clouds that would form the next generation, population 2 stars. Methuselah is one of those early descendants. That means it was born at a pivotal time in cosmic history. Not quite at the beginning, but close enough that its chemistry still carries the fingerprints of that primordial era. The low metallicity we see today is one clue, but the pattern of elements, which ratios of oxygen, iron and other heavy elements appear in its spectrum, tells an even deeper story. Certain element ratios match the expected output of early high-mass supernovae. In other words, Methuselah's birth cloud was enriched by only a few specific kinds of explosions, likely from stars dozens of times heavier than the Sun. This makes Methuselah a fossil star, not literally old enough to be part of the first generation, but built from the ashes of the first generation's deaths. Stars like it are some of the only surviving objects that can tell us what the first supernova were like, their energies, their masses, and how their debris mixed with the universe's primordial hydrogen. Then there's the matter of where Methuselah was born. Its path doesn't look like that of a normal Milky Way star. It does not move slowly in a circle around the center of the galaxy. Instead, it swings back and forth, going through the disk and into the galactic rim. There must be a great story behind that kind of motion. Perhaps the Milky Way began as a small dwarf galaxy that was torn apart long before it looked anything like it does now. If that's true, Methuselah isn't just a relic of the early universe. It's a traveler from a forgotten galaxy that didn't survive the Milky Way's violent growth. Its chemistry, orbit, and age together paint a picture of a star older than the modern structure of our galaxy, a star that has witnessed the Milky Way being built around it. Every time it loops past us, Methuselah is effectively time-traveling through the layers of the galaxy's history. It predates the thin disk. It predates the thick disk. It predates most of the halo. And depending on its exact age, it might predate the formation of the Milky Way itself. Parallax, why getting the distance wrong, wrecks everything. Before we talk about how old Methuselah was, we need to talk about how far away he was. If that number is even slightly off, the whole age estimate falls apart. In science, it's important to know how far away something is. Every other number is built on top of it. If you get it wrong, all the conclusions that follow will be wrong. Brightness, radius, temperature alignment, developmental stage, and the most important one, age. And Methuselah is such an old and chemically strange star that even a small change in distance can turn ancient survivor into impossible object. The most straightforward way to measure stellar distance is parallax, the tiny wobble in a star's apparent position as Earth orbits the Sun. The closer the star is, the bigger the wobble. For nearby stars, this shift is measurable. For something almost 200 light-years away, like Methuselah, the wobble is microscopic. We're talking fractions of a milliarc second. That's like measuring the width of a human hair from dozens of kilometers away. If your instruments are even slightly off, your final number will be wrong. Early distance measurements for Methuselah weren't great. Ground-based telescopes simply couldn't nail down a parallax that tiny with high precision. As a result, astronomers had distance estimates that varied enough to change the star's inferred brightness by large margins. And since a star's brightness is a direct ingredient in age dating calculations, These early uncertainties launched decades of confusion about Methuselah's true age. When the Hubble Space Telescope joined the picture, everything changed. The fine guidance sensors on Hubble were originally made to keep the telescope pointed straight. They turned out to be very accurate tools for measuring parallax. They gave scientists one of the most accurate distance readings ever for a star that old and faint when they used them on Methuselah. Astronomers no longer had to work with a vague range of possible lengths. Suddenly, they had a clear number, about 119 light-years, with small error bars. This should have made everything simpler. But instead, it caused an earthquake, because plugging that distance into the models made Methuselah brighter than earlier estimates. And brighter stars of this type correspond to older ages on the evolutionary tracks. That's how the 14.5 billion year estimate was born. Ironically, the better the distance, the worse the crisis appeared. But even Hubble isn't the end of the parallax story. Along came Gaia, a mission built to measure the positions, motions, and parallaxes of over 1 billion stars with accuracy no previous spacecraft could match. Gaia's data sharpened Methuselah's distance even further. The updated parallax suggested a slightly different luminosity, nudging the age estimate downward, closer to the universe's officially accepted age. Not enough to eliminate the tension completely, but enough to move Methuselah out of the impossible zone and into the barely permissible one. The catch is that systematic mistakes are very easy to spot in parallax readings with this level of accuracy. Even small changes in calibration, sensor distortions, or unmodelled movement can cause shifts that affect the whole process. When Gaia releases new data, it often comes with better calibrations, which means that older numbers are sometimes changed. Every change is important to Methuselah. A small change in the star's distance can have a big effect on its rebuilt luminosity. A different brightness means a different position on the Hertzsprung-Russell diagram, which means a different age. And this is where things get tricky. When scientists combine parallax uncertainties with uncertainties in metallicity, temperature, and helium content, they end up with an age range rather than a single number. Methuselah's revised ages now often fall somewhere between 12 and 14 billion years. That's within the margin of cosmic possibility, but still pressing right up against the ceiling. Fixing the universe age paradox. Scientists didn't freak out when they heard the shocking news that this star is older than the universe. Instead, they did some more math. Methuselah turned into a test of cosmic stress. If one star that was thought to be normal could push past the age of the universe, then all the assumptions about stellar physics, elemental abundances, and cosmic data had to be re-evaluated. Scientists found something interesting when they modified the numbers. The paradox wasn't caused by one big mistake. Many small assumptions all pointed to Methuselah being older, older, older. Start with the metallicity. Early measurements underestimated how much oxygen and other heavy elements the star actually contains. Even a small adjustment upward changes how efficiently the star transports energy from core to surface. That, in turn, affects where it appears on the evolutionary tracks, bringing its age estimate down by several 100 million years. Then there's helium. Helium abundance is almost impossible to measure directly in cool stars, like Methuselah, so astronomers have to guess based on models of early chemical enrichment. But if the helium fraction is even slightly higher or lower than assumed, the star evolves differently. A higher helium content generally makes the star evolve faster, meaning it would be younger than originally calculated. Stellar mixing effects add another layer of complexity. Over billions of years, heavier elements slowly sink toward the core while lighter elements float upward. This process, called gravitational settling, can make the surface appear more primitive than the star's interior actually is. If you assume the surface abundances represent the original composition, you're already making an incorrect assumption. one that artificially inflates the age. There's also the question of reaction rates. Nuclear fusion processes in stars rely on well-measured but not perfectly known reaction probabilities. Small updates to these values can shift the ages of metal-poor stars by hundreds of millions of years. Methuselah sits in the exact region of the HR diagram where these uncertainties matter most. It's at the point where small changes in the model inputs produce large shifts in predicted age. Then we come back to physics. We still can't get all scientists to agree on the Hubble constant, which tells us how old the universe is. The readings from faraway supernovae don't match up with the data from the cosmic microwave background. The universe might be older if the rate of growth is a little slower than thought. The universe might be younger if it moves faster. This stress is important for Methuselah because every change makes the goals different. When modern teams combine all these updated ingredients, better parallax, better metallicity, improved stellar models, refined reaction rates, and updated cosmological parameters, the result is far less dramatic than that early Hubble analysis suggested. Methuselah now falls in the 12 to 14 billion year range, depending on exactly which inputs you use. That means the star can coexist with a 13.8 billion year universe without breaking anything. But only just. What's intriguing about Methuselah is that current measures don't take away from the drama. They make it smaller. The star is no longer clearly breaking the rules of astronomy. Instead, it is now in a very narrow lane, where all assumptions must be true within very narrow limits for the age to make sense. Astronomers no longer believe that Methuselah shows that the Big Bang is not real. They don't think the problem is completely fixed, though. Instead, they see the star as a dashboard warning light that the physics of old, metal-poor stars may be more difficult than what current models show. What its chemical fingerprints reveal. A weak star is all you can see when you look at Methuselah through a telescope, but when scientists look at its light with a spectrograph, they see a chemical crime scene from the very beginning of the world. There is a story in Methuselah's spectrum that goes back before the Milky Way. And science doesn't lie, unlike measuring distance or model errors. Its marks show us what kinds of events created the cloud that turned into this star, how quickly galaxies formed in the beginning, and what the very first supernova were like. Start with the basics. Methuselah is extremely metal-poor. But that's only step one. What really matters is which elements are present and in what ratios. Stars of the early universe weren't born from a stew of dozens of heavy elements like the Sun. They were born from gas polluted by a handful of early supernovae, usually massive, short-lived population 3 stars. Those explosions each left behind a distinct signature. Some produced more oxygen than iron. Others produced more magnesium. Some pumped out heavy elements like strontium or barium in tiny amounts. By decoding this pattern, astronomers can reconstruct which kinds of first-generation stars lived, died, and detonated around Methuselah's birth cloud. In Methuselah's case, the oxygen-to-iron ratio is especially revealing. It's far higher than in younger stars, pointing to enrichment by massive, rapidly exploding supernovae. These weren't calm, steady burners. These were monsters that lived only a few million years before dying in violent core collapse events. And the debris from those earliest blasts mixed into the primordial hydrogen, providing just enough heavy elements for later stars, like Methuselah, to form. Methuselah's iron level is another important fact. It is very low, which means it is chemically pure. Iron by itself isn't enough, though. Scientists also look at metals that aren't as heavy, like magnesium and carbon. In the case of Methuselah, the pattern points to enrichment from just 1 or 2 supernovae, not dozens. That makes it very close to the second generation of stars that have ever been made. Not the first ones, because they didn't make it, but the ones that came right after them, into a universe that was just starting to play around with complexity. heavy R-process elements, like europium, are missing from Methuselah. These elements are usually made when neutron stars join or when supernovae explode very quickly and powerfully. Since those elements aren't found, it means that the universe is still too young for a lot of neutron star crashes to have happened. All of those things take time. Stars have to form, live, die, turn into neutron stars, find each other, and spin inward first. Methuselah was born before that time frame. On the flip side, some elements appear in slightly higher amounts than expected, which hints at mixing processes inside the star itself. Over billions of years, lighter elements drift upward, while heavier ones sink. This complicates things because the chemistry we observe today isn't perfectly identical to what the star was born with. Scientists have to reverse engineer this internal migration to estimate the original composition. And that original composition is what ties Methuselah directly to the earliest fireworks of the cosmos. On top of that, some unusual abundance ratios suggest that Methuselah formed in a region with limited mixing, meaning the gas cloud wasn't fully blended with the wider galaxy. This supports the idea that Methuselah may not have formed in the Milky Way at all, but inside a small primitive dwarf galaxy that the Milky Way later cannibalized. Those smaller galaxies tend to have simplified chemical evolution, producing stars with cleaner and more extreme chemical signatures. Everything about Methuselah's chemistry screams early universe. From its ultra-low iron levels, to its oxygen-rich profile, to the absence of heavy neutron capture elements, to the pattern of intermediate metals, Methuselah is a snapshot of a cosmic era we can't observe directly anymore, because the stars from that time are gone. Only their descendants survive. A star from the galactic halo. Methuselah doesn't live in the Milky Way's nice organized towns, which is where the sun hangs out. It lives in the galactic halo, which is a huge, old, low-density shell that forms a ghostly bubble around the galaxy. Some of the oldest things in the universe can be found here, including globular clusters, stars with almost no metal, and the remains of small galaxies that the Milky Way destroyed long before humans were born. If the Milky Way were a city, the ring would be the empty lots where old areas used to be. And Methuselah's house is one of the few that is still standing. To understand why this matters, you need to know the architecture of the galaxy. The thin disk, where stars like the Sun live, is young. It formed relatively late, once the galaxy settled into a stable, rotating structure. The thick disk is older, populated by stars a few billion years older than the Sun. But the halo is ancient. It formed during the galaxy's wildest, most chaotic years, when it was still absorbing smaller galaxies, smashing star clusters together, and growing through violent mergers. Methuselah fits perfectly into this environment. Its extremely low metallicity, unusual orbit, and ancient age all point to a halo origin. But the details of its orbit make it even more interesting. Instead of gliding in a gentle circle around the Milky Way's center like the Sun, Methuselah flies through space on a highly elongated plunging orbit. It dives through the galactic plane at high speed, shoots far above the disk, then swings back down again. It's like a comet, except instead of ice and dust, it's a star older than almost anything else we've ever found. This kind of orbit is a huge red flag, in a good way. It tells astronomers that Methuselah did not form where it is today. It likely formed in a small dwarf galaxy outside the Milky Way. Billions of years ago, as the Milky Way grew, it pulled that dwarf galaxy in, tore it apart, and scattered its stars across the halo. Methuselah is one of the survivors. Think of it as cosmic collateral, a star caught up in the gravitational violence of the galaxy's earliest mergers. Many stars like this are left over from galaxies that have been dead for a long time. What they are made of, how old they are, and how they circle each other all show how the Milky Way grew. But Methuselah stands out even among stars with halos. Its orbit is so stretched out, energetic, and not lined up with the disk that it suggests it has been around for a very long time, maybe even before the main structure of the Milky Way was formed. Another clue is its speed. Methuselah moves fast, much faster than most disk stars. High speed is typical for halo stars because they're not part of the orderly rotational flow. Instead, they freely orbit the galactic center in all directions, left over from a time before the galaxy flattened. Methuselah's velocity, combined with its orbit, suggests it has been traveling like this for over 12 billion years. This star has literally watched the Milky Way assemble around it. When Methuselah was born, the galaxy probably didn't resemble a spiral at all. It might have looked like a chaotic cloud of gas and dark matter with a few early star clusters. Over billions of years, as the Milky Way absorbed smaller galaxies and spun itself into a spiral, Methuselah simply kept looping through space on its ancient trajectory, unaffected by the grand design forming beneath it. The halo also explains why Methuselah remained so metal-poor. Stars born in dwarf galaxies generally have lower metallicities because those galaxies produce fewer massive stars and fewer supernovae. With less chemical enrichment, the stars stay primitive. When the Milky Way consumed those galaxies, their metal-poor stars ended up sprinkled throughout the halo, including Methuselah. Did it come from a cannibalized galaxy? As researchers learn more about Methuselah's past, it gets harder to believe that it was born in the early Milky Way. The way it works, how fast it moves, how shiny it is, and the ratios of its elements all point to a much more exciting origin story. The most violent theory also makes the most sense. Methuselah may have come from a small galaxy that the Milky Way broke up billions of years ago. To understand how this works, picture the early Milky Way not as the graceful spiral we see in photographs today, but as a messy pile of building blocks flying toward each other. Galaxies in the early universe behaved more like hungry animals than elegant structures. They collided, merged, swallowed, and shredded each other in enormous gravitational battles. When a large galaxy like the Milky Way encountered a smaller one, the smaller galaxy rarely survived. Its gas was stripped, its stars were scattered, and its core was torn apart. And the pieces, the stars, were thrown into wide, looping orbits around the growing galactic halo. Methuselah's orbit fits that story perfectly. It doesn't follow the rotational flow of the disk. Instead, it slices through the galaxy at a steep angle, diving through the plane and whipping far out into the halo. Orbits like that are chaotic, stretched, and misaligned. Exactly what you see in stars that were once part of a different galaxy. These orphaned stars retain the motion of their original system, even after their home galaxy has been destroyed. But the strongest evidence isn't its orbit. It's the chemical fingerprint Methuselah carries inside its light. Dwarf galaxies have slow, inefficient star formation. They produce fewer massive stars and fewer supernovae, which means they enrich their gas much more slowly than a big galaxy. Their stars tend to be extremely metal-poor, even when the universe is well into its later epochs. Methuselah's metallicity is so low, and its element ratios so specific, that it resembles stars found in ancient dwarf galaxies far more than stars formed within the Milky Way's early structure. Take the oxygen to iron ratio, for example. Methuselah is rich in oxygen relative to its iron content. That pattern typically forms when a single, massive supernova enriches a gas cloud, rather than dozens contributing to a blended environment. This single supernova signature is very common in tiny galaxies, where only a handful of stars ever formed. In the Milky Way, by contrast, enrichment happened fast and chaotically through thousands of explosions. The fingerprints of early stars formed here tend to be more mixed. Methuselah looks too pristine. Then there's the question of R-process elements, the heavy ones produced in neutron star mergers. Methuselah barely has any. That suggests its birth environment existed before neutron star mergers became common enough to enrich galaxies significantly. Dwarf galaxies, especially the ultra-faint ones, often show this exact pattern: high ratios of light elements, low ratios of heavy ones, and almost no indication of R-process enrichment. It's the chemical signature of a galaxy that lived fast, produced a few massive stars, and died early. Methuselah's orbit also hints at the nature of its lost home. The most dramatic galaxy mergers leave behind stellar streams, long ribbons of stars that once belonged to a smaller galaxy. Over billions of years, these streams fade, smear, and dissolve into the halo. But their orbits remain distinctive. Methuselah's path through the galaxy matches the kind of orbit associated with ancient, fully disrupted systems, especially ones that collided when the Milky Way was still soft and unstructured. Scans of how galaxies form give this idea even more support. Models show that stars like Methuselah, which have the same chemicals and circling behavior, almost always come from outside the main galaxy. As early as a billion years after the Big Bang, some of them merge and fall together. They join the halo before the disk even forms. The Milky Way has taken in a lot of these kinds of galaxies. Most of them haven't left any obvious signs behind except for their stars. There's a good chance that Methuselah was one of those refugees. It becomes not just a relic of the early universe, but a surviving member of one of the first galaxies the Milky Way ever destroyed. That gives astronomers a rare opportunity. By studying Methuselah's chemistry and motion, they can reconstruct the properties of a galaxy that no longer exists. They can estimate how big it was, how fast it formed stars, and how quickly it died. And from there, they can understand how the Milky Way grew, not smoothly, but violently, by consuming its neighbours. Another possibility is that Methuselah might not be the only one who is different. A lot of halo stars might be old immigrants, and each one brings a piece of the chemical DNA from a lost galaxy. By looking at how old the stars are and what they are made of, scientists can piece together the history of galaxy cannibalism, a series of mergers that shaped our universe before the Sun was born. Methuselah is one of the oldest pieces of any galaxy that has been found. Its age may be close to that of the universe's earlier periods. It's not just a stone star. It is the rest of a galaxy that is very old. Scientists are still not sure which old merger Methuselah might have been a part of. Was it a small proto-galaxy that broke apart completely? It might have come from a middling dwarf system that was pulled in soon after the Big Bang. Or was it a part of something bigger, like Gaia sausage Enceladus, a huge galaxy that the Milky Way ate up 10 billion years ago? The truth may be somewhere in the middle, but most of the proof points to the fact that this star is not local. Why its orbit is so weird. It is thought that if Methuselah were a normal star, it would move in a smooth circle path around the Milky Way, following the disk's steady spin. But this star is not normal in any way, not even its path. Astronomers knew right away that Methuselah must have come from a strange place because it hurtled through the sky like a stone being thrown through the air. To understand why its orbit is such a big deal, imagine the Milky Way as a giant spinning wheel. Most stars, including the Sun, are like beads glued to the wheel's surface. They move around the centre smoothly, forming a thin, flat disk. Their orbits are stable, slow-changing and well-behaved. Methuselah is nothing like that. Its orbit is elongated, tilted and plunging. Instead of staying near the disk, it shoots far above and below it, looping deep into the galactic halo before diving back in. This kind of orbit is a cosmic red flag. It screams that the star doesn't belong to the disk population at all. Halo stars have eccentric orbits, but even among them, Methuselah is an outlier. It travels fast, cuts through the galaxy at awkward angles, and passes through regions where disk stars never go. This chaotic behaviour offers a few vital clues. First, it tells us that Methuselah is ancient. The galaxy's halo was built early in its history, long before the disk flattened into its modern spiral shape. Stars born in that era tend to retain wild orbits because they formed in a much more turbulent environment. Even more telling is Methuselah's orbit, which shows that it didn't come from the Milky Way at all. When stars are taken from smaller galaxies, they often keep the rotational features of their original systems, which weren't lined up with the disk of the Milky Way. The stars from those galaxies were thrown into the halo on strange, looping paths when the Milky Way ate them up. This design is almost exactly what Methuselah's circle looks like. Its speed is another sign. Methuselah moves a lot faster than most disk stars. Halo stars don't have to follow the disk's steady spin, so they can move at this high speed. But Methuselah's motion is so fast that it suggests a dramatic gravitational past, possibly involving close calls with the huge structures at the centre of the galaxy, or with pieces of old mergers. Simulations of stellar dynamics show that stars with Methuselah-like orbits often originate in highly disrupted systems. They were pulled into the Milky Way in the early universe, thrown onto eccentric paths, and left to wander the galactic halo ever since. Over billions of years, these orbits evolved slightly due to gravitational interactions, but the chaotic signature remains. The star's motion also helps explain its survival. Stars like Methuselah spend most of their lives far from the dense disk, where most destructive events occur: supernova shocks, molecular cloud collisions, radiation storms, and strong gravitational perturbations. Its orbit keeps it isolated, almost in a protective bubble of emptiness. This isolation may be one reason it has remained intact for so long, preserving its primitive chemistry rather than being contaminated by later galactic processes. The most fascinating part about Methuselah's orbit might be what it says about time. The star's current path is a record of an event that happened a long time ago, when the Milky Way was still young. It tells the story of a merger that happened so long ago that the galaxy has eaten up all but the stars of the dwarf galaxy that caused the merger. Astronomers can figure out how the Milky Way's gravitational field changed over time by looking at Methuselah's path. This shows how the galaxy grew, moved, and settled. Testing Big Bang cosmology with one star. It seemed like one of the most stable numbers in astronomy before scientists ever looked through their telescopes at Methuselah. 13.8 billion years, a clean, exact number that is backed up by readings of the cosmic microwave background, studies of galaxies, and the math of how the universe is expanding. It seemed like the number would never change. Then one small, faint star showed up and didn't care at all about how sure cosmologists were. Methuselah didn't just teeter on the edges of that timeline, it pushed right up against it, making experts wonder how solid that number really was. The reason Methuselah became such a stress test is simple. The age of the universe is not measured directly. It is inferred from the behaviour of the universe today. We measure the expansion rate, the Hubble constant, the density of matter and dark energy, and the temperature ripples in the cosmic microwave background, then work backward through equations describing cosmic evolution. If any one of those numbers is slightly wrong, the entire timeline shifts. So when a star comes along that seems to be older than the universe computed from those parameters, a serious question emerges. Did we miscalculate the universe? Or the star? The first step was obvious. Check whether the star's age estimate could be wrong. But as scientists dug deeper, they realized they needed to check something bigger. Whether the cosmology could be wrong. Methuselah became a kind of cosmic audit. If the universe's behaviour was misunderstood in even small ways, this one star would expose it. Cosmologists began by reopening the question of the Hubble constant, the measurement that sets the expansion rate of the universe. Around the same time, Methuselah's controversial age was being discussed. Two different methods of measuring the Hubble constant began to disagree sharply. One method relied on distant supernovae and galaxy distances. The other came from the cosmic microwave background measured by the Planck satellite. The fact that these two methods gave different answers hinted at a deeper tension, and Methuselah's age only made the tension louder. If the universe expanded faster than assumed, it would be younger. If it expanded more slowly, it would be older. And depending on which method astronomers trusted, the universe's age could swing by several 100 million years. That's not enough to make Methuselah firmly older than the universe, but it's enough to blur the boundary between impossible and barely allowed. Then came the question of dark energy. The universe has been accelerating in its expansion for the last several billion years, and that acceleration is driven by dark energy, a mysterious force we still barely understand. If the behavior of dark energy has changed over time, or if our model of it is too simple, the age of the universe could shift again. A universe with slightly different dark energy dynamics could be older, giving Methuselah more room to exist. People looked into everything, even the early world. Could a new meaning be given to the cosmic microwave background? Could early inflation models need to be changed? Was there something missing from the estimates for the basic elements? Cosmologists kept coming back to these questions, and Methuselah was always there as a quiet reminder. Your answers must match this star, or something is wrong. But in the end, the world wasn't easily swayed. The Big Bang model stayed strong. The cosmic radio background didn't change. The universe's age could change a little, based on what people thought, but it never changed enough to make Methuselah younger. That left scientists with a remarkable conclusion. The star wasn't disproving the Big Bang, it was tightening it. Methuselah forced cosmologists to sharpen their models, refine their parameters, and confront the disagreements in the Hubble constant. It didn't break the Big Bang theory, it forced it to evolve. That's kind of how science is meant to work, though. There is a difference between theories that are strong because no one questions them, and theories that are strong because even the biggest opponents can't bring them down. Methuselah was that challenger, a single piece of information that made cosmology's most important number prove itself. Tension with the Hubble constant. The debate over the Hubble constant is one of the most important ones in modern science. This will help you figure out what went wrong with Methuselah. We think the universe is a certain age because of this number, which tells us how fast the universe is expanding. If the rate of growth is faster, the universe must be younger, since it got this big so much faster. As the rate of growth slows down, the world gets older. There are two very good ways to measure that rate of growth right now, but they give different answers. On one side is the distance ladder method, which builds the expansion rate using nearby stars, Cepheid variables, and type Urea supernovae. This method tends to produce a higher value of the Hubble constant, which implies a younger universe. On the other side is the cosmic microwave background measurement, which uses early universe physics to project the expansion rate forward. This produces a lower Hubble constant, meaning an older universe. These two answers are far enough apart that they can't both be right. And into this disagreement walked the Methuselah star, carrying a potential age that brushed right against the older universe estimate. Before Methuselah's age was refined, its 14 billion plus central estimate aligned better with a slow expanding older universe. But that contradicted the faster expansion implied by supernova measurements. Suddenly, this star wasn't just a curiosity. It became a piece of a much larger puzzle known as the Hubble tension, a conflict that remains unresolved to this day. Methuselah's age forced astronomers to confront the idea that maybe the universe really was older than the younger estimate implied. Maybe the cosmic microwave background measurements were pointing to the correct model, and the supernova distance ladder was missing something. If that were true, Methuselah would fit comfortably within a slightly older universe. But as more data came in, things only became more complicated. Gaia refined parallax distances for supernova host galaxies, strengthening the distance ladder. Meanwhile, improvements in early universe physics confirmed the cosmic microwave background's predicted expansion rate. Both sides became more precise, and yet they remained incompatible. Methuselah's refined age offered no decisive answer. If its age had stayed firmly above 14 billion years, cosmologists might have used it as a weapon against the younger universe interpretation. But once its age estimate narrowed, Methuselah lost its power to pick a side. Still, there is friction, and Methuselah is still being talked about. It's still close enough to the age of the universe for Methuselah to have been possible, no matter which way is right. If the idea of a universe that is younger and growing quickly is right, then Methuselah was probably younger than most people think. If the older model of the world slowly growing is right, Methuselah can be near the top. The star doesn't end the fight, but it does make both sides be honest. And that honesty is essential, because the Hubble tension might be the biggest clue we have that some part of our cosmological model is incomplete. Some astronomers believe the tension points to new physics. Maybe dark energy behaves differently over time, or maybe there's an unknown early universe ingredient we haven't accounted for. Others argue the tension comes from overlooked measurement errors. In either case, the Methuselah star is a reminder that stars, not equations, ultimately decide what is true about the universe. Numbers can be recalculated, models can be rewritten, but a star shining in the sky is real. What its temperature and luminosity tell us. Astronomers were looking at something much easier and more worrisome long before the arguments about cosmology, dark energy, and the Hubble constant. Methuselah's temperature and brightness did not fit what models of stellar evolution said they should be. Scientists put Methuselah in a strange spot on the Hertzsprung-Russell diagram, which shows the life stages of stars. It looked like it was in the wrong class at the wrong time. That spot was the first sign that something wasn't right, and it's still one of the most important pieces of proof for how this star almost broke the rules of science. To understand the significance, you have to think of the HR diagram as a giant set of railroad tracks, each one representing a star's life path. A star's temperature, which we measure through its colour and spectrum, tells us how hot its surface is. Its luminosity, which we calculate from apparent brightness and distance, tells us how much energy it emits. Together, these two values reveal exactly what stage of life a star is in. For stars like Methuselah, metal-poor subgiants, this stage is very sensitive to age. Even small shifts in luminosity or temperature correspond to significant differences in how long the star has been alive. Methuselah is hotter than the Sun, but only slightly more luminous. That combination puts it in the subgiant region, where stars have exhausted the hydrogen in their core and are gradually transitioning toward becoming red giants. Subgiant stars are excellent chronometers because they evolve rapidly during this phase. A star may spend billions of years on the main sequence, but only a few 100 million years in the subgiant lane. So if you catch a star there, you can read its age with unusually fine precision. But Methuselah didn't line up nicely with any of the expected tracks. For its temperature and luminosity to make sense, the models predicted an age older than allowed by cosmology. Something in the formulas had to give: the opacity, the mixing length, the helium content, the metallicity, the temperature calibration, or the distance. Every small factor influenced where Methuselah landed on the HR diagram. And when the early calculations placed it directly above the 13.8 billion year limit, it created a contradiction that demanded attention at every level of astronomy. The problem was not that the star looked outrageously bright or faint. The issue was that multiplying tiny uncertainties created a huge effect. Say its distance was off by a few percent. That could shift its luminosity enough to change its age by 1 billion years. Say its oxygen abundance was underestimated by a fraction. Suddenly, the stellar tracks shift. Say the temperature had an unnoticed calibration drift. The star jumps into a region meant for older or younger stars. All these uncertainties stacked together made Methuselah look like an impossible object. A key concept here is metallicity. Metal-poor stars like Methuselah shine slightly differently from metal-rich stars because their interiors allow energy to escape more efficiently. With fewer heavy elements to block radiation, metal-poor stars are hotter and brighter at the same mass. This changes how the star climbs off the main sequence. When scientists plugged in the earliest metallicity estimates for Methuselah, which were too low, the star ended up in a position on the HR diagram that corresponded to absurd ages. Updating those metallicity values shifted the star downward into a more reasonable region. Taking data of temperature adds another layer. In the past, colour indexes were used to figure out the temperatures of stars. However, these indexes are affected by dust, device calibration, and theories about the star's atmosphere. Even a few dozen degrees difference in Methuselah's temperature would cause its spot on the map to move. Later, more advanced spectral tests helped get a better idea of the temperature, which lowered the age. That's why most models today put Methuselah's age between 12 and 14 billion years old, rather than well above 14 billion years old. Even then, the star remains precariously perched near the edge. Subgiants really are that sensitive. A small change in energy transport physics, such as an update to how convection works in metal-poor stars, can move their evolutionary path significantly. Methuselah sits right where the theoretical tracks are steepest and most uncertain. That means its age is especially vulnerable to small errors in luminosity or temperature, and explains why the star became the centre of one of the largest cosmology controversies in recent memory. Methuselah's temperature and luminosity not only challenge our understanding, but also confirm something else. The star genuinely is ancient. It cannot be a few billion years old. It cannot be an intermediate age halo star. Its position on the HR diagram locks it firmly into the category of early universe survivors. Whether it's 12 billion or 13.5, Methuselah's location leaves no room for a youthful interpretation. The star is old, profoundly old, and every model agrees. Scientists disagree on how old people are in that range, but no one doubts the fact that the star is a relic from the very beginning of the universe, based on its warmth and brightness. Astronomers had to work hard to improve their models because this point was almost past the timeline of the universe. The role of stellar physics uncertainties. It's humbling to realise that even our best models of stellar evolution, which have been worked on for decades, put through a lot of tests, and are used to guess the ages of thousands of stars, can be thrown off by small doubts. It's not that physics is wrong, it's because stars, especially subgiants that are low on metal like Methuselah, are in a part of parameter space where everything gets stronger. The estimated age can be off by hundreds of millions of years if there is a small doubt about an unknown response rate. If a star is very old, very close to the cosmic roof, those unknowns become hard to ignore. The first major source of uncertainty lies in nuclear reaction rates. Stars generate energy through fusion, but the precise rates at which certain reactions occur are measured experimentally in laboratories, often at energies far from the conditions inside stellar cores. This means scientists must extrapolate. If the reaction rate for a crucial process, such as the proton-proton chain or the CNO cycle, is slightly off, the star's internal temperature gradient shifts. That change alters how quickly the star evolves off the main sequence. For a star like Methuselah, this can mean the difference between a 12 billion year age estimate and a 13.5 billion year one. Another major factor is opacity, the resistance of stellar material to the flow of radiation. Opacity controls how heat moves from the core to the surface. Heavy elements, even in tiny quantities, significantly alter opacity. If the opacity tables used in models underestimate the effect of certain elements at low metallicity, the star will appear to age differently. When Methuselah first broke the universe's age limit, some astronomers suspected the opacity calculations were partly responsible. Updated opacity models have slightly revised the stellar tracks, helping reconcile the star with cosmological expectations. Then there's convection, the movement of hot plasma inside stars. Convection is notoriously difficult to model because it depends on turbulence, mixing and heat exchange processes that cannot be fully simulated inside a star's enormous chaotic interior. Instead, astronomers use simplified models with adjustable parameters, such as the mixing length. Changing this parameter alters how efficiently the star transports energy. For metal-poor stars like Methuselah, small adjustments can shift their predicted ages significantly. In fact, differences between various stellar evolution codes often arise from different choices in convection treatment. Microscopic diffusion, the slow settling of heavier elements toward the core, adds yet another layer. Over billions of years, helium and metals sink, while hydrogen rises. This changes the star's internal composition, which changes its energy transport, which changes its evolution. If diffusion is underestimated, Methuselah's surface metallicity looks more primitive than its interior actually is, leading models to place it too high on the age scale. More recent models include stronger diffusion and turbulence corrections, lowering the star's predicted age. Even the helium percent, which is just one number, has big effects. Helium is the second most common element in stars, but it is very hard to measure in cool stars, like Methuselah. Scientists have to guess based on models of how chemicals changed in the early universe. But Methuselah's growth would go faster if it started with a little more helium than was thought. That means a star that seemed to be 14 billion years old, based on old ideas, might be more like 12.5 billion years old. Methuselah's age has gone down as predictions of helium have gotten better. All of these unknowns affect each other. There are a lot of parameters in the star models, and each one has a small error bar. All of these parameters work together to make a web of sensitivities. Methuselah is in a place where the web gets tighter. It doesn't matter what. There is a mark left by every belief. That's why the star became a focus point. It showed us what we don't know about the insides of stars, and made astrophysicists face the limits of their models. Despite all these uncertainties, reaction rates, opacities, convection, diffusion, helium fractions, the overall picture remains the same. Methuselah is ancient enough to challenge cosmology, ancient enough to force refinements in stellar physics, ancient enough that even the newer models place it among the oldest stars ever found. The uncertainties may shift its exact age, but they never erase its significance. How heavy elements change the clock. Methuselah almost shattered our ideas about how old the world is. To understand why, look closely at something that seems so simple: its chemistry. Not the vague idea that it is metal poor, but the hard numbers that show how many heavy elements it actually has, and how those elements have affected every part of its growth. Heavy elements make up a very small part of the mass of stars, like the Sun, that are full of metals, but they have a huge impact on how energy moves inside the star. It's even more important in a very old star like Methuselah, where heavy elements are almost non-existent. When the amount of metal in a star is that low, its whole evolutionary path changes. And if you use the wrong amount of metal in your model, the age guess can be off by hundreds of millions of years. To see why, picture energy trying to get out of the center of a star. Heavy elements spread, absorb, and stop radiation, making them work like tiny walls. The inside of a star gets cloudier as it includes more metals. Light has a hard time getting through. Heat gets stuck, and the top layers change to make up for it. This is not what happens when a star has almost no metals, like Methuselah's. It is easier for energy to leave. At the same point of development, this makes the star hotter, smaller and brighter than its metal-rich twin. In other words, you can't just plug Methuselah into a model that works for everyone. If you don't have a model made just for stars with very few metals, the age estimate will be wrong from the start. The trouble is that metallicity is not just one number. Astronomers measure many different element ratios: oxygen to iron, magnesium to iron, barium to iron, and so on, each one affecting the star's opacity in slightly different ways. Oxygen plays an especially important role because it is one of the dominant contributors to opacity in metal-poor stars. If you underestimate the oxygen abundance, the models treat the star as even more primitive than it really is, pushing its predicted age upward. That is exactly what happened in the early analyses of Methuselah. The oxygen content was underestimated, and the star appeared to evolve too slowly. Correcting the oxygen measurement tightened the age, shaving hundreds of millions of years off the original estimate. But heavy elements influence more than just opacity. They change how the star's core heats up over time, which affects how quickly it runs through its hydrogen supply. Metals also influence how convection behaves, the churning motion that transports energy from deeper layers to the surface. With fewer heavy elements, convection becomes more important in particular regions of the star. Small changes in convection models can therefore alter the star's entire evolutionary timeline. When Methuselah first stunned astrophysicists, it wasn't just because the metallicity was low. It was because the exact combination of elements, the ratios, placed it in a region where many important physical processes become highly sensitive. Diffusion adds another layer of complexity. As time goes on, heavy parts of a star slowly sink toward the center, while lighter parts rise to the edges. The process is very slow, but it's important. The surface makeup we see now is not the makeup Methuselah had when he was born. The models will not work if you think that the surface metallicity shows how the star was when it was first formed. The star looked older than it really was because the first estimates of its age didn't fully take this diffusion effect into account. The difference is less noticeable in newer types because they have better internal mixing. The models got more correct, not Methuselah getting younger all of a sudden. The importance of metallicity becomes even more striking when you consider how early the star formed. If Methuselah is truly one of the oldest stars in the universe, then it was born from gas, enriched by only one or two massive supernovae. That means its heavy element content carries the signature of very specific explosions. These first supernovae may have produced unusual element ratios that are rare in modern stars. But those ratios shape how Methuselah has evolved for nearly 14 billion years. If you misinterpret those ratios, the clock you build from them will tell you the wrong time. This is why Methuselah became such a scientific headache. Its metallicity was low enough to make every detail matter, but not low enough to be simple. Ultra-metal-poor stars often follow very straightforward patterns, produced by a single dominant enrichment event. Methuselah sits in the middle, primitive enough to be ancient, but complex enough to complicate the models. Its heavy element pattern isn't chaotic, but it is unusual. That unusual pattern requires models that handle metal-poor evolution with precision. And when models improve, Methuselah's age shifts accordingly. Methuselah's metal tells a story beyond its age, which is both frustrating and beautiful. It tells us what was going on in the universe when the star was born. It tells us which close supernova went off, how big they were, how furiously they died, and how their debris mixed with the early universe. The star is almost younger than the universe's age limit, which shows how long ago those events must have happened. The metallic taste isn't a bother, it's a sign. The helium problem inside Methuselah. Helium is Methuselah's silent enemy. It's the element that looks easy but makes everything harder. Helium is one of the most important things that scientists use to figure out how old a star is. It's also the hardest to measure. Metals like iron and oxygen leave clear traces in a star's spectrum, but helium stubbornly refuses to show itself. Helium absorption lines are hard to see in stars as cool as Methuselah. So, scientists can't find out how much helium the star had when it was first formed. This is one of the most dangerous parts of science, because they have to guess. This is especially true for a star this old and sensitive. The amount of helium in the universe may not seem important, but it has a big impact on how stars burn their fuel. When it is born, a star with more helium changes more quickly. It heats up more quickly. Different contracts make up its heart. Its brightness goes up at different times. If you change the helium fraction by a small amount, the star can move between age tracks. This is why the connections between a star's mass, composition, and development are usually pretty easy to figure out. But there is very little room for mistake when it comes to Methuselah. A few percent change in the amount of helium can change the age by hundreds of millions of years. Models of the early universe give us a starting point. Big Bang nucleosynthesis predicts that the early cosmos contained about 24% helium by mass. That number is one of the most robust predictions of cosmology. But stars do not always follow the cosmic average. Their birth material can be enriched or diluted depending on which supernovae exploded nearby. Massive stars synthesize helium and spew it into space when they die. If Methuselah's birth cloud was enriched by a single massive supernova, it could have contained more helium than the primordial norm. And if that extra helium isn't accounted for, the star's estimated age becomes artificially inflated. Then there's the issue of diffusion. Over billions of years, helium slowly sinks toward the core. That means the surface helium abundance today is lower than what the star had at birth. If you model Methuselah with its current helium content instead of the original, the calculated age becomes skewed. Modern stellar models attempt to correct for this, but the exact amount of diffusion that has occurred is still uncertain. The physics of turbulent mixing in the outer layers of metal-poor stars remains one of the least understood parts of stellar evolution. For Methuselah, that uncertainty matters immensely. The helium metallicity link is another puzzle. This is the idea that galaxies slowly build up helium as they gain stronger elements. This connection might not work perfectly because Methuselah was born early. In the earliest epochs, the universe may have produced helium in bursts tied to the deaths of the first massive stars, not in the smooth progression seen in younger galaxies. If the helium in Methuselah came from one of those early bursts, then its development did not follow the path that current models predict. The helium problem extends deeper into the star's core. Helium affects the temperature gradient inside the star, which controls how quickly it exhausts its hydrogen supply. Since Methuselah is currently in the subgiant phase, a phase where tiny differences in core structure produce huge differences in luminosity, helium becomes one of the most decisive variables in the age calculation. If scientists underestimate the helium fraction, the star appears too old. If they overestimate it, the star appears too young. Methuselah sits in the delicate middle ground, where the true helium content must be pinned down to extraordinary precision. But even though helium is nearly invisible in the spectrum, astronomers have indirect ways to estimate it. They examine related elements whose abundances hint at the kind of supernova enrichment the star experienced. They compare Methuselah's spectrum to theoretical models of early supernova yields. They calculate the diffusion history by modelling gravitational settling over billions of years. Each of these steps narrows the possible helium range and narrows the age estimate along with it. In recent years, more advanced stellar evolution codes have incorporated increasingly sophisticated helium physics. These models treat convection, diffusion, and opacities with greater nuance than older codes. When Methuselah is run through these updated models, its age typically falls between 12 and 14 billion years, depending on the exact helium fraction used. That range is still breathtakingly close to the age of the universe, but it no longer exceeds it outright. Helium refinements didn't magically fix Methuselah. They made it more consistent with cosmology while keeping it ancient enough to matter. Why subgiant stars are nature's best clocks. There would have been no trouble if Methuselah had been a main sequence star like the Sun. Main sequence stars are not good at telling time. For billions of years, they have been in the same area of the Hertzsprung-Russell map, barely moving as the hydrogen in their cores slowly fuses together. If you look at a main sequence star for all of your life, you would never see a change that is important to development. Because they are so stable, they can help us understand how stars are put together, but not how old something is. At 4 billion years, a star like the Sun can look very much like it does at 9 billion years. The timeline gets fuzzy. But Methuselah isn't in the main sequence anymore. It's a subgiant, a star that has just run out of hydrogen in its core and is beginning the journey toward becoming a red giant. In this brief evolutionary phase, the star experiences one of the most dramatic transformations of its entire life. The core contracts, the outer layers expand, the luminosity rises, the temperature shifts. All of these changes happen on a relatively tight schedule, which turns subgiants into something precious, cosmic clocks with short, readable timescales. This is why Methuselah became such a powerful age probe. Subgiant stars move through their evolutionary phase in only a few 100 million years. A blink of an eye compared to the billions of years they spend in the main sequence. Their location on the HR diagram is therefore extremely sensitive to age. A small shift in luminosity means a big jump or drop in age. That's great when your measurements are precise, but it's terrifying when one of the measurements pushes you over the universe's age limit. Methuselah sat right in that sensitive band, and its measured brightness placed it at an age that seemed to break the timeline of the cosmos. Another reason subgiants make good clocks is that they don't suffer from some of the degeneracies that plague other types of stars. Red giants, for example, all look saturated, large, luminous, and temperature stable, no matter their exact age. White dwarfs are great cosmic clocks, but require understanding their entire cooling history, which becomes messy if you don't know the star's original mass or metallicity. Main sequence turn-off points in star clusters can yield precise ages, but that only works when you have thousands of stars with identical birth conditions. A solitary field subgiant like Methuselah avoids these problems. Its temperature, luminosity, and metallicity feed directly into stellar evolution models in a way that yields a fairly sharp age estimate, at least compared to most other types of stars. That sharpness is exactly what made Methuselah dangerous. When you feed in numbers and the models return an age older than the universe, you can't hand-wave it away. A subgiant's evolutionary state won't let you. The sensitivity of this phase also magnifies the importance of distance. A tiny revision in parallax, the measurement of how far away the star is, changes the star's luminosity enough to push the age estimate by hundreds of millions of years. This is partly why Methuselah's age seemed to jump around as Hubble, and later Gaia, improved distance measurements. Every improvement nudged the star along the subgiant track, sometimes shaving off age, sometimes adding it back. Its low metallicity adds another complication. Metal-poor subgiants evolved differently from metal-rich ones. With fewer heavy elements trapping radiation inside, the core cools and heats differently, and the envelope responds more dramatically. As a result, the subgiant track steepens. You get an even greater change in luminosity for a given change in age. That makes metal-poor subgiants extraordinary clocks, and also extraordinarily sensitive to modelling uncertainties. Because of this sensitivity, Methuselah turned into a storm. It was almost out of the main sequence, in one of the best times to figure out how old something is, and had one of the lowest metallicities of any halo star that is known. It was like a pressure point in astrophysics. Lightly press it and you get a clear signal. Press it wrong and everything hurts. Astronomers used that sensitivity to refine their models. Methuselah forced improvements in opacity calculations, diffusion physics, convection modelling, helium assumptions, and more accurate parallax corrections. In many ways, it became the benchmark subgiant. The star's extreme age made it a test case for everything we think we know about the early evolution of low metallicity stars. Gravitational settling and mixing. One big reason why it's been so hard to figure out how old Methuselah is that its skin doesn't tell the whole story. Astronomers figure out what a star is made of by looking at the chemistry of its top layers. But those layers don't always show what the star was made of when it was born. Over billions of years, stars slowly move things around inside them. This is called gravity settling, also written as diffusion. Helium, iron, and oxygen are heavy elements that slowly move toward the center of the galaxy. Lighter elements, on the other hand, move upward. It's a slow but steady process that changes the star's surface look in small ways. But the deep inside tells a very different story. This matters enormously for age calculations. Stellar evolution models depend on initial chemical composition. If the surface shows lower metal content than the star actually started with, the models will misinterpret the star as more primitive, and therefore older. Early studies of Methuselah treated its present-day metallicity as a direct measure of its birth composition. That assumption turned out to be flawed. When diffusion was properly included, Methuselah's estimated original metallicity was higher than the surface suggested, and the star's age shifted downward. But diffusion is not the only internal process at play. Stars also experience mixing, turbulence and convection that churn the outer layers and counteract some of the sedimentation happening deeper inside. In stars with higher metallicity, the outer convective zone is deeper, which stirs the material more effectively and slows the settling of heavy elements. But in extremely metal-poor stars like Methuselah, the convective envelope is shallow. There's less churning, so gravitational settling operates more efficiently. This means Methuselah's surface composition has drifted farther from its original state than it would have if the star were richer in heavy elements. The tricky part is that scientists cannot observe these internal processes directly. They must infer them through models and simulations. These models depend on assumptions about how efficiently turbulence mixes the stellar layers, how fast elements settle, and how rotation affects internal currents. Small changes in these assumptions can produce large changes in the inferred initial composition. And because Methuselah's evolutionary stage is so sensitive to composition, those changes propagate directly into its age. Diffusion and mixing don't work the same way for all elements, which made Methuselah's job extra hard. Different things sink at different rates. Some metals react more strongly with radiation, which can make them float in the air. This is known as thermal levitation. When these effects happen in stars with low metallicity, they are hard to predict. It's possible that iron will settle faster than air. Helium and magnesium may move in different ways. Each of these small changes helps with figuring out opacity, which helps with building models for moving energy, which helps with guessing how old something is. When scientists finally began including more sophisticated diffusion and mixing models in their age calculations for Methuselah, the star's apparent age dropped, sometimes by hundreds of millions of years. This didn't make Methuselah young. It simply moved the star from seemingly older than the universe to almost as old as the universe, but still allowed. The star remained ancient, one of the oldest known, but it no longer demanded a rewrite of cosmological history. Even now, diffusion remains one of the biggest contributors to uncertainty in the star's age. That's because the efficiency of settling depends on physics that is still only partly understood. Magnetic fields, rotation rates, turbulence in the convective zone, and even subtle interactions between ions at high temperatures. These are not small corrections. They shape the entire trajectory of a star's evolution and determine how its surface will look billions of years later. Methuselah's gravitational settling also interacts with another challenge. Its orbit through the galaxy exposes it to different stellar environments. As it plunges through the Milky Way's disk, it encounters changing tidal forces that may influence how its outer layers behave. While these effects are subtle, they add yet another layer of complexity when reconstructing the star's birth conditions. Yet despite these complications, diffusion has become one of the clearest explanations for why Methuselah seemed impossible at first. It wasn't that the universe was younger than we thought. It was that the star's surface had lied to us. The chemistry we observed was incomplete. The true story, the initial mixture of metals and helium that determined the star's evolution, was hidden beneath billions of years' worth of quiet rearrangement. Astronomers had to improve diffusion physics all over the field because of Methuselah's case. They had to admit that even small things going on inside a star can change its whole past. It made the models that are used to study halo stars, globular clusters, and the communities of stars in dwarf galaxies more accurate. It also turned a once simple idea, that the composition of the surface matches the makeup at birth, into a warning story. How Methuselah challenges stellar evolution codes. People who write codes for stellar evolution have been quietly worried about Methuselah for a long time, long before it was called the star older than the universe and made the news. Astrophysics is based on these codes, which are used to build huge computer models that show how stars live, age, heat up, get brighter, grow, and finally die. We use them to base every estimate we make about stars. The numbers also work great for most stars. When you put in mass, metallicity, and makeup, a nice evolved track that fits with reality comes out. When scientists first fed Methuselah's data into these codes, something happened that no astrophysicist likes to see. The model couldn't find a good match. It could make the star younger if it ignored the metallicity. It could make the metallicity right if it ignored the luminosity. It could fit the temperature if it cheated the helium fraction. It could fit the age by pushing reaction rates to the edge of their uncertainty. But it couldn't make everything line up at the same time. That's when people realized Methuselah wasn't just an old star, it was a stress test. A star that lived so close to the edge of cosmic history that it pushed every part of the model to its breaking point. The core problem is that stellar evolution codes were mostly built and calibrated using stars like the Sun, younger halo stars, globular clusters, and metal-rich populations where decades of observation keep the models grounded. Extremely metal-poor subgiants like Methuselah exist in a different regime. In that regime, small uncertainties in opacity, diffusion, helium abundance, convection, and nuclear reaction rates explode into huge differences in predicted luminosity and age. Take opacity tables. Opacity determines how easily radiation escapes from the interior. The tables used in stellar models are massive libraries built from quantum mechanical calculations and laboratory experiments. But for the earliest, most metal-poor stars, the opacity depends on elements present in minuscule amounts, often near the limit of measurement. If those opacities are off even slightly, Methuselah jumps dramatically on the H-R diagram, and suddenly the star looks a billion years older than it should. Then there's convective modelling. Convection is messy. It's turbulence, heat transport, and chaotic plasma motion all mixed together. Stellar codes don't simulate it directly. They use simplified approximations like mixing length theory, which introduces adjustable parameters. For most stars, Changing those parameters barely affects the story. But for a star as metal-poor as Methuselah, convection changes everything. The temperature structure, the luminosity rise, the rate at which the envelope expands during the subgiant phase. A different mixing length can shift the inferred age by enough to cross the boundary of the universe's age. Nuclear reaction networks also play a role. The rates of certain key reactions, especially in the proton-proton chain, which dominates low metallicity stars, are measured experimentally but always with uncertainties. Those uncertainties ripple through evolution tracks. For a star like Methuselah, where every billion years matters, that ripple becomes a wave. The codes also have to simulate diffusion, the slow gravitational settling of helium and heavier elements into the core. The rate of diffusion can't be measured from the surface. It's buried deep inside, and modelers must include assumptions about turbulence, microscopic motions, and radiative levitation. Methuselah sits right in the region where diffusion strongly alters the surface composition, and that makes the initial composition, the one used in the model, extremely uncertain. If you assume the wrong helium fraction or the wrong original metallicity, the track shifts again. The worst thing about Methuselah, though, was that all of his mistakes went in the same direction. The age went up because of all the unknowns, like distance, metallicity, convection, opacity, helium, and diffusion. That alignment was not a fluke. It meant that these codes for star development had never been pushed this far in this environment before. The models couldn't handle Methuselah because he was too strong, didn't have enough metal, was too old, or lived in the early world. So scientists improved the codes. They updated opacity calculations, refined diffusion equations, improved nuclear cross-sections, recalibrated convection parameters, used Gaia's superior distance measurements, and re-evaluated early universe helium predictions. Each update nudged Methuselah's age closer to the acceptable side of cosmology, bringing the models and the data into better alignment. So what's the catch? Methuselah is still right on the edge, even with all those changes. It doesn't fit right. I don't like this star. It still makes the codes work on the edge of what they can mimic. In this way, Methuselah does something very uncommon. It shows us what we don't know. Comparing Methuselah with other ancient stars. People often say that Methuselah is the oldest star we've found and that it almost broke the rules of astronomy. In the early world, though, it's not by itself. It is part of a small but growing group of stars that formed soon after the Big Bang. Each one holds information about the conditions in that very early time. Putting Methuselah next to these other very old stars helps us understand what makes it special and how it fits into a much bigger story about the universe. The earliest stars we know about fall broadly into two categories: extremely metal-poor subgiants, like Methuselah, and ultra-metal-poor dwarfs found in the halo and bulge. These stars share a defining trait. They contain almost no heavy elements. The fewer the metals, the older the star tends to be, because heavy elements hadn't yet been manufactured by generations of supernovae. But within this family, Methuselah stands out. Its metallicity is low, but not the lowest known. Some halo stars have metallicities 1,000 or even 10,000 times lower than the Sun. Yet those hypermetal-poor stars aren't necessarily older. Many are still on the main sequence, where age is harder to determine. They're chemically ancient, but their exact ages are fuzzy. Methuselah, on the other hand, is in the perfect evolutionary phase, subgiant, where age becomes sharply readable. That combination of very metal-poor and easily age-measurable is rare. Globular clusters offer another comparison. These dense balls of ancient stars orbiting the galaxy contain some of the oldest known stellar populations. Many globular clusters have ages around 12 to 13 billion years, close to Methuselah's range. But globular clusters have advantages Methuselah doesn't. Thousands of stars born at the same time allow astronomers to fit their entire population on an HR diagram and infer collective ages. Methuselah, by contrast, is a single field star. It has no siblings to compare against. Its age must be derived entirely from its own light, a more delicate and error-prone process. Yet even compared to globular clusters, Methuselah is extreme. Most clusters show slightly higher metallicity, meaning they formed after a few more supernovae enriched the galactic environment. Methuselah's lower metallicity suggests it formed before many of those clusters or outside the Milky Way altogether, inside a dwarf galaxy that never reached the same enrichment level. Other ancient halo stars like HD 122563 or BD plus 17 degrees 3248 share similar ultra-low metal content and halo orbits. But these stars often fall into different evolutionary stages, making their ages harder to constrain precisely. Methuselah's status as a subgiant once again gives it the edge, a clean, sharp age indicator instead of the broad estimates typical for main sequence or giant branch halo stars. Then there are the carbon-enhanced metal-poor stars, CEM stars, which contain bizarrely high levels of carbon relative to iron. These stars likely formed after just one or two supernovae polluted the early gas with unusual element ratios. While they may be as old or older than Methuselah, the exotic chemistry complicates the modelling. Methuselah, with a more normal set of element ratios, for the early universe at least, avoids some of those uncertainties and yields a clearer age. When compared to these other ancient stars, Methuselah becomes something else entirely, a benchmark, a reference point for what an extremely old, moderately enriched subgiant should look like. It calibrates the entire population of ancient halo stars. Scientists use Methuselah's refined models to reinterpret the ages of other ancient stars, adjusting their expectations about how metal-poor stars behave during early evolution. Methuselah also stands apart because of its orbit. Many ancient stars follow halo orbits, but not all have such extreme plunging trajectories. Methuselah's path through the galaxy, high above the disk, deep into the halo, looping back through the plane, signals an origin tied to an early galactic merger. That adds a layer of historical significance. It's not just old, it's a surviving witness from the era when the Milky Way was still forming, still eating smaller galaxies, still figuring out its shape. Put simply, other ancient stars tell us the universe was old. Methuselah tells us how old. Other ancient stars tell us supernovae enriched the early universe. Methuselah tells us which supernovae did it. Other ancient stars hint at early galaxy formation. Methuselah reveals when those galaxies merged. It is the star that connects all the dots. It might not be the oldest star ever found. New finds could make it older. But it is the oldest star whose age we can figure out with a high level of accuracy. So it is the centre of the early world sequence. Clues about the first supernova explosions. Before the Milky Way and before galaxies took on the shapes we see today, the universe was home to a generation of stars that were so big and burned out so quickly that none of them are still around. People called these stars Population 3 giants. They were huge, metal-free stars that burned hot, lived quickly, and burst furiously. We are not able to see them directly. They are no longer there. But their ashes are still there, locked up in the second generation of stars that were made from their pieces. Methuselah is one of these remains from the second group. Astronomers study its science, not just Methuselah, but also the first supernova that ever happened in the world. Every massive star that dies in a supernova leaves behind a chemical fingerprint. The proportions of oxygen, magnesium, carbon, calcium, and iron reveal how hot the explosion was, how rapidly the star burned, how violently it died, and what mass it had at birth. When astronomers examine Methuselah's spectrum, what they're really pulling out is a chemical autopsy of the early universe. Its light is encoded with the identities of the stars that came before it, stars that lived and died only a few 100 million years after the Big Bang. Methuselah's unusually high oxygen to iron ratio is one of the biggest clues. Massive early supernovae tend to produce lots of oxygen and little iron. That's because their cores burn incredibly hot and expel huge amounts of alpha elements, oxygen, magnesium, silicon, while iron, which forms later in the process, emerges in smaller quantities unless the explosion is especially energetic. The high oxygen content in Methuselah suggests that the star formed from gas enriched by at least one extremely massive progenitor, probably 20 to 40 times the mass of the Sun. Those early monsters lived only a few million years, then seeded the universe with its first heavy elements. Another key ratio involves magnesium and silicon. These elements appear in Methuselah in proportions consistent with a very specific kind of supernova, a high-energy core collapse event. This hints that the first supernovae to pollute Methuselah's birth cloud weren't gentle explosions. They were violent, asymmetric, possibly jet-driven, and capable of distributing elements over large regions of primordial space. These signatures match theoretical predictions of early supernova models, which suggest that population 3 stars often died in hypernova-like explosions far more energetic than most modern supernova. Methuselah contains almost no heavy R process elements like europium or samarium. These are created in neutron-rich environments, usually in neutron star mergers or rare types of supernova involving exotic physics. The scarcity of these elements in Methuselah shows that the star formed before neutron star mergers became common in the universe. That means Methuselah's birth likely predates the time when the first binary neutron stars had finished spiraling together, a process that takes hundreds of millions of years. So Methuselah's composition provides a lower bound for when the earliest neutron star mergers began influencing galactic chemistry. Methuselah also shows signs of alpha enhancement, a pattern typical of early generations of stars created when only the most massive supernovae existed. These supernovae produce large quantities of alpha elements but relatively small amounts of iron peak elements. That's exactly what Methuselah displays. This suggests that the gas cloud it formed from was touched by only 1 or 2 early supernovae, not dozens, not hundreds. And that simplicity is what makes Methuselah so valuable. Stars formed from heavily mixed gas clouds become chemically confusing. Stars formed from 1 or 2 events become readable. Even the star's strange carbon levels have a story to tell. Unlike many very old stars, Methuselah is not in the group of stars that are carbon enhanced and metal poor. It has a modest amount of carbon instead. That means that the supernovae that came before it weren't the strange, faint supernovae that are thought to make a lot of carbon. The birth cloud of Methuselah, on the other hand, seems to have been filled with more typical massive supernovae, which are consistent with stars with 20 to 40 solar masses that explode through standard core collapse. All of these facts come together to make a strong story. The supernovae that woke up Methuselah weren't soft. They were huge, fast, early, and full of energy. They were the very first people in the universe to really make elements. Methuselah came from a cloud of gas that was made richer by the universe's first successful attempt to make heavy elements. It wasn't from the unstable environment that formed later after many cycles of supernova recycling. What it says about early Milky Way assembly. There's more to Methuselah than just the first supernovae. In its early stages, the Milky Way wasn't the pretty spiral galaxy we see in pictures. It was a rough, crazy mess more than 12 billion years ago. When Methuselah was born, the Milky Way wasn't even a galaxy in the way we think of them today. It seemed like a cloud of dark matter, gas, and broken dwarf galaxies that were going against gravity and coming together. Based on his age, chemical and position, we can figure out when that assembly began, how disorganized it was, and what kinds of building blocks made up our galaxy. The first clue comes from Methuselah's position in the galactic halo. Halo stars are the oldest in the galaxy, and their orbits record the fossilized motions of the Milky Way's earliest assembly events. Methuselah's orbit is elongated and plunging, suggesting that it was part of the galaxy during or shortly after the earliest mergers. Stars with these extreme halo orbits often came from dwarf galaxies consumed during the first billion years of the Milky Way's growth. That means Methuselah's very existence proves that the Milky Way began assembling extremely early, almost immediately after the first stars formed. Its age reinforces that point. If Methuselah is around 13 billion years old and the universe is 13.8 billion years old, then the Milky Way must have started gathering material less than 1 billion years after the Big Bang. That places the Milky Way among the earliest large galaxies to assemble. It also means the conditions for star formation, cold gas clouds, gravitational wells, and the first heavy elements must have existed very early in our region of the universe. The chemical signatures inside Methuselah provide more detail. Its metallicity is low, but not zero. That suggests it formed after the very first generation of stars exploded, but before enrichment became widespread. In other words, it formed right at the beginning of the Milky Way's assembly sequence, when gas clouds had been polluted by only a handful of early massive stars. This puts Methuselah at the transition point between the population 3 era and the era of early dwarf galaxy formation. The rotation of Methuselah adds an additional layer. It goes through the galactic plane instead of going around and around inside the disk, which means that the disk of the Milky Way did not exist when Methuselah was born. After the chaos died down and the galaxy started to spin normally, the disk formed. Methuselah lived before things became stable. In the early days of the Milky Way, when it wasn't sure what shape it would take, this is what it looked like. The star's motion also hints at the kind of mergers that built the galaxy. Large mergers tend to leave behind coherent streams of stars. Smaller mergers scatter stars more randomly. Methuselah's extreme orbit suggests a small, early dwarf galaxy, one that was shredded so completely that almost none of its original structure survives. This kind of merger was common in the early universe, when small galaxies formed quickly and were swallowed just as quickly. After that, there's the matter of chemistry differences. If you look at modern galaxies, you can see that as you move toward the center, the stars get more metal-rich, but Methuselah's low metallicity shows that it formed before there were such differences. It was from a galaxy where chemical development had just begun. Each heavy element atom in that galaxy can be traced back to 1 or 2 early supernovae. This means that the star is a picture of the Milky Way before it had shape, a disk, arms, and the wide range of chemicals that we now take for granted. Methuselah also connects to the era of globular cluster formation. Some of the oldest globular clusters in the Milky Way have ages around 12.5 to 13 billion years. Methuselah's age overlap suggests that both it and those clusters formed around the same time, during the galaxy's initial starburst phase. But Methuselah formed alone, outside the dense cluster environments. Its solitary nature suggests that the early Milky Way hosted multiple modes of star formation: cluster-based, dwarf galaxy-based, and isolated star formation inside primitive gas clouds. It is now clear that Methuselah is not only a piece of the early universe, but also of the early Milky Way. Its existence shows that the galaxy was busy putting together and making stars before the universe was even a few 100 million years old. It tells us that the Milky Way didn't grow slowly. It grew quickly by merging and adding to itself. We can learn from it that our galaxy grew by eating smaller galaxies. It also tells us that the process started a lot earlier than many models thought. Methuselah versus globular cluster. If Methuselah is one of the oldest stars ever found, then the next question that comes to mind is how it stacks up against the largest groups of stars in the Milky Way. Some of the oldest structures in the galaxy are globular clusters, which are huge spheres packed tight with hundreds of thousands of stars that were all born at the same time and are changing at the same rate. Unlike single field stars, globular clusters show how the universe was in its early stages. Scientists can be much more sure of their ages because they can look at the turn-off points of thousands of stars in each cluster using the Hertzsprung-Russell map. This lets them figure out an exact age for the whole population of stars, not just one subgiant. For decades, globular clusters were considered the oldest entities we could measure reliably. Many cluster ages hover around 12 to 13 billion years. Some of the most ancient, M92, M15, NGC 6397, have ages pushing up against the 13 billion year line. Before Methuselah complicated everything, these globular clusters were used as benchmarks for calibrating the age of the universe itself. If the universe is 13.8 billion years old, it makes sense for the oldest globular clusters to sit just below that limit. And, interestingly, most do. But Methuselah threatened to break that coherence. When its initial age was calculated at 14.5 billion years, it stood outside the entire evolutionary framework implied by globular clusters. If Methuselah truly were older than them by 1 billion years or more, it would imply that some stars formed before the earliest globular clusters, before the epoch when galaxies began assembling themselves through mergers and starbursts. That possibility was unsettling because globular clusters are often considered the first large-scale star-forming events in a galaxy's life. A star older than the clusters would suggest an even earlier mode of star formation, smaller, more isolated, less structured, happening before clusters existed. As Methuselah's age estimates were refined, something interesting happened. The star drifted downward into an age range much closer to the clusters. Modern calculations place Methuselah between about 12 and 14 billion years old. That range fits within the cluster timeline, although it still presses right up against the upper limit. What matters is that Methuselah no longer sits above the globular cluster population in a way that forces cosmology into a corner. Instead, it now acts as a corroborating data point that supports the general astrophysical picture. The Milky Way formed its earliest stars and its earliest clusters within the first billion years of cosmic history. Globular clusters have chemical compositions that reflect a more heavily enriched environment than Methuselah. Their stars often show evidence of multiple generations of stellar formation, internal chemical pollution, and complex evolutionary histories. Methuselah, with its simpler chemistry, likely formed even earlier, possibly in a dwarf galaxy or gas cloud that had not yet undergone the layered enrichment that clusters typically show. This difference suggests that Methuselah was born either before or outside the environments that produced the first massive clusters. In other words, Methuselah may not be older than the oldest globular clusters, but it likely represents a different lineage. Clusters were born in dense environments where star formation happened in large bursts. Methuselah could have emerged in a sparse environment, a nearly pristine gas cloud, lightly enriched and quickly forming only a few stars before dispersing. It may have belonged to a small proto-galaxy that the Milky Way later devoured. This interpretation fits perfectly with its extreme orbit, its chemical simplicity, and its metal-poor nature. The connection between Methuselah and globular clusters tells us more. The early universe did not form stars in a single, regular way. Some stars were born in huge explosions that made the thick groups we can still see today. Others quietly formed in small areas of gas. Methuselah is the fossil that shows where those pockets were. Globular groups are fossils that show that the bigger bursts happened. Models improvements with asteroseismology. Asteroseismology, the study of measuring starquakes, is a strong tool that astronomers could use to solve the Methuselah puzzle one day. Seismologists study earthquakes to learn more about the inside of Earth. Asteroseismologists study tiny changes on the surface of a star to get a picture of what's going on inside it. These changes show the star's density profile, inner structure, internal makeup, convection zones, and even how old it is. Listening to starquakes in thousands of stars with projects like Kepler and TESS has changed the way we think about the life cycles of stars in the last 10 years. Yet Methuselah remains out of reach. Why? Because asteroseismology works best for stars that are bright, nearby, and relatively large. Subgiants and giants are perfect targets because they oscillate loudly. Their surfaces ripple with detectable waves. But Methuselah, despite being nearby in cosmic terms, is faint in the photometric sense. Its brightness is too low for current space telescopes to measure oscillations at the precision needed. Even though the star is physically close enough for parallax measurement, it is not bright enough for high-quality seismic data. But imagine if we could get past that obstacle. Astronomers would finally be able to get what they've been looking for: a direct reading of the star's internal structure, free of many of the errors that plague current models. It would no longer be so important to use temperature calibrations, chemistry assumptions, opacity tables, or diffusion changes to figure out the age. Instead, it would be anchored to the star's actual internal density profile, which evolves predictably over time. The ages of stars that are figured out by earthquakes are often very accurate, within a few % at most. That could mean being able to tell the difference between 12 billion years and 13.5 billion years with a level of sharpness that has never been seen before for a star as old as Methuselah. The promise of future missions is precisely this. They might finally make Methuselah loud enough to listen to. Next-generation telescopes designed for high-precision photometry, missions like Plato, or even ground-based networks using advanced adaptive optics, could gather the long, continuous observations needed to detect faint oscillations. Longer baselines mean lower noise. Better detectors mean higher sensitivity. Methuselah is not impossible. It's merely at the edge of what current technology can hear. But even if future instruments can detect its oscillations, there's another complication. Asteroseismology is most accurate when combined with detailed spectroscopic information and precise distances. Methuselah's distance is already well constrained by Gaia, and its spectrum has been studied extensively. What remains uncertain is its helium content, diffusion history, and internal mixing processes. Exactly the kinds of things seismic measurements could illuminate. Seismic frequencies reveal the sound speed profile within the star, which depends directly on helium abundance and core composition. In short, starquakes could reveal Methuselah's inner truth. Its faintness is not the only challenge. Because Methuselah is a metal-poor star, its oscillation amplitudes may differ from those of better-studied metal-rich stars. Metal content affects convection, which in turn affects the surface granulation patterns that drive observable oscillations. If early universe stars behave differently in this regard, current seismic scaling relations, formulas calibrated on nearby Sun-like stars, may not translate cleanly. Scientists would need to develop new metal-poor seismic models to interpret Methuselah's oscillations correctly. Because of this, Methuselah is both interesting and unsettling. It's just on the edge of being able to measure earthquake activity. It's close, but not clear. It's old and quiet. Very important, but just out of reach for technology. They haven't given up yet though. Some people say that Methuselah might become a better target if it gets brighter as it moves toward the red big branch later in its life. Others think that we will finally be able to pick up on its faint movements when optical sensitivity gets better, like it could with PLATO or the Roman Space Telescope. The impact of Gaia's next data releases. One project, Gaia, has changed the way we think about Methuselah over and over again. The age of the universe's most controversial star changes a little each time Gaia puts out a new set of data. Sometimes it changes by tens of millions of years, and other times it changes by more. To explain this, we only need to look at how far away Methuselah was. Distance tells you about luminosity. Luminosity tells you about evolutionary stage, and evolutionary stage tells you about age. If you get the distance wrong by even a small amount, the age estimate starts to change. Gaia's strength is ultra-precise astrometry, the ability to measure the positions, parallaxes, and proper motions of stars with a precision that previous missions could only dream of. Before Gaia, Methuselah's distance was measured using the Hubble Space Telescope's fine guidance sensors. That was a major step forward at the time, but still came with uncertainties. When Gaia DR2 arrived, its parallax refinements nudged the star's luminosity downward, helping push its age estimate back under the cosmic limit. Later releases sharpened the numbers further, tightening the error bars and reducing the wiggle room in every interpretation. But the story is far from over. The next Gaia releases will include even finer parallax corrections, improved calibration of systematic errors, better handling of chromatic effects, and a more complete correction for instrument motion over time. These improvements matter because Methuselah is perched in the most sensitive region of the H-R diagram. Its age calculation reacts sharply to even the smallest shifts in luminosity. A parallax difference of only a few microarc seconds can move the inferred luminosity enough to adjust the star's age by hundreds of millions of years. Even its motion through the galaxy matters. Gaia's proper motion data helps reconstruct Methuselah's orbit, an orbit that hints at its extragalactic origin and the epoch of its capture by the Milky Way. Improved motion data means refined orbital models, and refined orbital models hint at the star's gravitational history, whether it has interacted with dense regions or been through tidal forces that may have influenced its internal structure in subtle ways. While these effects are secondary to the luminosity-age relationship, they do feed into how astronomers interpret Methuselah's long-term evolution. Future Gaia data will also refine the star's binarity constraints. Even a faint, undetected companion, a small white dwarf for example, could affect the star's motion or apparent brightness. While current evidence strongly suggests that Methuselah is solitary, Gaia's sensitivity may eventually confirm this beyond doubt. If a companion existed and contributed even a tiny amount of light, it would alter the luminosity estimate and therefore the age. Better parallax also makes it possible to calibrate other old stars. People often compare Methuselah to other halo subgiants, but if their parallaxes change, the whole age scale might need to be adjusted. It is Gaia's job to not only improve Methuselah's distance, but also to provide a wider astrometric context, which is a web of distances and movements for thousands of ancient stars that can all be compared to improve our understanding of the early universe's timeline. One of the most expected changes is Gaia's work to make instrument models and chromatic correction better. Methuselah's spectrum is not like that of most reference stars because it is very low in metals. In other words, older parallax measures might have slightly gotten the centroid point wrong when different colours of light were used. Gaia's newest models are meant to fix that problem. A better, more accurate parallax for Methuselah could be obtained by making small changes to how the telescope corrects for errors caused by wavelength. If that parallax shifts even slightly higher, the star becomes closer, fainter and younger. If it shifts lower, the star becomes farther, brighter and older. Either direction will refine or reopen the debate about whether Methuselah sits within or just outside the universe's age limit. Most scientists expect Gaia's improvements to further tighten Methuselah's age into the 12.3 to 13.3 billion year range. But it's also possible that the next data release will nudge the star back toward the upper extreme, renewing the tension between stellar evolution and cosmology. The real power of Gaia is that it turns Methuselah from a troublemaker who lives alone into a part of a group that has scientific value. Astronomers will be able to draw the earliest stages of star formation with a level of detail that has never been seen before. Once dozens or even hundreds of halo subgiants have parallaxes on the same level as Gaia. Methuselah will still be important, maybe even the standard, but it won't be the only thing that goes wrong. This picture will be part of a set that shows how the Milky Way's chemistry and structure have changed since the beginning of time. Cosmic chronometers, stars as timekeepers. One of the most important things that the Methuselah star does is make us think about a simple but shocking idea. Stars are clocks, not clocks in a roundabout way. They are literally cosmic clocks that keep track of time over billions of years in ways that tell us about the past of the universe. Methuselah is the most dramatic example of this. He was a star whose age is so far beyond what the universe can handle that it makes us question everything we think we know about how time works in the universe. The concept of using stars as clocks isn't new. Astronomers have long used main sequence turn-offs in globular clusters to estimate ages. But individual stars, especially subgiants, are far more precise timekeepers, provided we can understand their internal physics. Methuselah became the flagship of this method. Its luminosity, temperature, metallicity, and evolutionary state turn it into a clock so finely balanced that even small uncertainties become magnified. That sensitivity is both a blessing and a curse. It makes Methuselah incredibly informative and incredibly difficult to interpret. Cosmic chronometers work because stars evolve in predictable ways. The rate at which they burn hydrogen, the pace at which they exhaust their core fuel, the speed at which they move into the subgiant phase, all depend on physical constants and initial composition. If you know those starting conditions, and if your models are accurate, you can calculate how long the star has been around. Methuselah's age is not guessed. It is calculated from first principles, even though every ingredient in the calculation must be measured with extreme precision. Methuselah then starts to teach there. It is very clear to us where our models work well and where they don't. It shows how important it is to figure out opacity, helium content, diffusion, reaction rates, convection physics, and measure distance. The Methuselah is very strict. If you don't model every part of stellar development properly, the time it gives you won't make sense. That being said, it also shows something deeper. The universe is full of these clocks, each subgiant in the ring that is low on metal, every old giant in a circular group, every very low-mass dwarf in the cosmic bulge. Each one has a mark from the time when the universe first let stars form. It's not that Methuselah was the oldest person ever, it's that he was the oldest person who could be measured. Future telescopes will identify thousands more stars like Methuselah. With Gaia's precision parallaxes, with Plato's potential seismic measurements, and with next-generation spectrographs capable of reading faint chemical signatures, astronomers will build a network of cosmic timepieces stretching across the halo. These clocks will allow us to map the sequence of star formation events, reconstruct the assembly of the Milky Way, and probe the early enrichment history of the universe. The idea that stars are chronometers also has consequences for cosmology. If the older stars consistently sit at the edge of the universe's timeline, they force cosmologists to refine the expansion rate, the dark energy equation of state, and the interpretation of early universe physics. If the older stars turn out younger than expected, they validate the current cosmological model. Stars become anchors for universal truth, independent checks on the mathematics of cosmic evolution. There is a line between what we know and what we are still learning, and Methuselah is the first of these lines. It makes us think about how precise we need to be to understand the first billion years of the world. It shows that the past of the universe is written not only in galaxies and background radiation, but also in the quiet, faint stars that move through the halo on long paths. The title "Oldest Star Ever Found" is catchy, but it's also misleading. It has changed how people think about Methuselah in ways that don't match the slow, careful reality of stellar astrophysics. Subtleties get lost in headlines. They take a star whose age ranges are complicated and have been measured over many years and turn it into a cosmic miracle, a star that is older than the universe. It was never meant that way, though. It's much more interesting to know what they meant and what Methuselah really stands for than just a record-breaking name. The first misunderstanding comes from how we talk about stellar ages. When astronomers say Methuselah is about 14 billion years old, they don't mean exactly 14 billion years, carved in stone. They mean that when the star's temperature, luminosity, metallicity, and models are plugged into the equations, the best fit solution lands near that number, with uncertainties both above and below. In the earlier studies, that central value landed above the 13.8 billion year age of the universe, creating the famous paradox. But even then, the error bars were large enough that the star could be younger. The phrase "older than the universe" was never meant to be taken literally. It was meant to highlight the tension in the measurements, the thin line between what we observe and what our models allow. Another source of confusion comes from how stars evolve. Most of the time, we cannot measure the exact age of a star. We measure an age range. The boundaries of that range are shaped by everything from distance uncertainties to reaction rate tables. Methuselah sits right at the top of that range, but other ancient stars sit there too. There are stars in globular clusters that approach 13 billion years. There are ultra-metal-poor halo stars whose chemistry suggests birth dates shortly after the first supernovae. Methuselah's uniqueness is not that it is older than all of them, but that its evolutionary phase, the subgiant stage, made its age easier to measure sharply. Headlines often miss that distinction. Cosmology, which studies the universe's large-scale structure, cosmic microwave background, and rate of growth, tells us how old the universe is. Astrophysics, specifically stellar development, chemical abundances, and brightness, tell us how old Methuselah was. Different tools and ideas are used in these areas. It didn't mean that the star was physically older when its age seemed to be longer than the age of the universe. It showed that two different areas of science were arguing about something very close to the truth. The mistake made by the public was to think there was a straight disagreement when there was actually a problem with calibrating across disciplines. Even now, with refined measurements, headlines remain simplistic. When new estimates placed Methuselah closer to 13 billion years, some outlets declared the mystery solved. Others declared the star debunked as the oldest. Both are misunderstandings. Methuselah is still one of the oldest stars ever measured precisely. It still sits near the cosmic age limit. It still pushes every part of our models to their highest precision. Its age wasn't debunked, it was tightened. The truth is that the oldest star narrative hides the deeper significance. Methuselah matters not because of a specific number, but because of how many parts of astrophysics it touches. It forces improvements in nuclear reaction rates, helium estimation, opacity calculations, diffusion models, and parallax measurements. It reflected, and still reflects, the unresolved tension in cosmology over the Hubble constant. It serves as a benchmark for early galaxy formation, supernova enrichment, and halo star orbits. It's not important to know if Methuselah is the oldest star. The real story is that it showed how close the age of the universe is to the age of the first stars. It proved that star creation started incredibly early, maybe even less than 200 million years after the Big Bang. It proved that the Milky Way started to form faster than many models thought it would. It showed that old stars are labs for studying the physics of the early universe in a way that astronomy can't. How close we came to a real crisis. The idea that Methuselah might be older than the world was talked about in papers, at conferences, and in debates for a short time in the history of astronomy. Not just a little bit older, quite a bit bigger. It's about 14.5 billion years old, and there are some doubts that it's not even close to the accepted cosmic limit of 13.8 billion years. Astrophysics and cosmology were looking at each other across a fault line at that point. The scientific community had to ask, what if the paradox was real? It's worth understanding what would have happened had Methuselah's age held steady above the universe's age. The first casualty would have been cosmology itself, not the entire Big Bang model, but the precision with which we calculate cosmic time. The universe's age comes from models tied to the cosmic microwave background, early universe physics, and the Hubble constant. If multiple independent stars, especially well-measured subgiants like Methuselah, had revealed ages older than that, cosmologists would have been forced to revisit the most fundamental parameters of the universe: the expansion rate, the density of dark energy, the matter of content, the curvature, everything that feeds into the cosmic age formula. A genuine contradiction would have meant the universe is older than we thought, but adjusting the universe's age upward is not simple. A small increase requires rebalancing many parts of the model. A large increase could have implied new physics, exotic dark energy behavior, modifications to expansion histories, or even additional components in the early universe that slowed cosmic evolution. Methuselah almost pushed us there. This also means that the first stars would have had to form earlier than any model suggested. At this point, cosmologists think that the first stars formed about 200 to 300 million years after the Big Bang. If Methuselah had been really 14.5 billion years old, the first stars would have formed even earlier, maybe in a time when the universe wasn't dense or cool enough for gravity to cause it to fall. That would go against what the early universe knew about physics. Before recombination, something had to change in the way matter acted. This change would have been felt in all theories, from dark matter to CMB interpretations. Then there's the impact on galactic evolution. If Methuselah were older than the oldest globular clusters, astronomers would have needed to explain why the oldest clusters formed so late. A star older than the clusters implies a different lineage of star formation: solitary, sparse, non-clustered, occurring before the era when gravity began forming massive stellar nurseries. This would mean the early universe wasn't a gradual ramp-up into star formation, but a chaotic environment where occasional stars formed in isolation long before larger structures took shape. And if the contradiction had persisted, it would have demanded that stellar evolution models were missing something profound. The equations that govern nuclear fusion, convection, opacity, mixing, and diffusion might have required revision at the fundamental level. Perhaps metal-poor stars evolved differently. Perhaps fusion rates at extremely low metallicity were off. Perhaps helium physics in the early universe needed rethinking. A persistent age conflict would force astrophysicists to consider that stars don't evolve as predictably as we thought, especially stars born in the primordial era. The real crisis would have been interdisciplinary. Cosmologists would argue the universe must be older. Stellar physicists would argue the star must be younger. Observational astronomers would point to parallax uncertainties. Nuclear physicists would re-examine reaction cross-sections. No one field could solve the problem alone, because the contradiction touched every layer of cosmic science. Science was getting ready for the worst in some ways. At some workshops, people talked about both the Hubble strain and the Methuselah problem at the same time. Some studies suggested changes to the opacities of stars. Some people pushed for early models of dark energy. Some people wondered if cosmic chronometers might be pointing to a problem with the usual picture of the universe. And then, slowly, the numbers shifted. Better parallax, better oxygen abundance, better diffusion modelling, better reaction rates. Methuselah slid downward, still old, still extreme, still sitting right at the cosmic ceiling, but no longer beyond it. The crisis evaporated, replaced by a sharpened understanding of early stellar evolution and improved confidence in the universe's age. The limits of current stellar models. Some progress has been made in modelling Methuselah, but there is a harsh truth at the heart of the matter. The physics of how stars evolve wasn't designed to work well at the very edge of cosmic time. It took stars like the Sun, globular cluster populations, or red giants with ages between a few 100 million and 10 billion years to build and test most stellar models. In the field of stellar astronomy, these stars are in the safe zone. They are not too close to the cosmic boundary or too far from the extreme low metallicity regime to cause big problems. That's not where Methuselah lives though. It lives on the very edge, where even small flaws in the models can cause huge changes in how old it is thought to be. The first limit of current stellar models is their treatment of extremely metal-poor stars. The earliest versions of stellar evolution codes handled low metallicity reasonably well, but reasonably well collapses when working with stars whose metallicities are fractions of fractions of fractions of the Sun's. The opacity tables used in stellar interiors depend heavily on metal content. If the opacity is wrong by even a few percent at Methuselah's composition, it changes the star's luminosity evolution enough to shift the age estimate by hundreds of millions of years. And because Methuselah's metallicity is so low, opacity is dominated by just a handful of elements, especially oxygen. This makes the models hypersensitive to how those elements absorb and scatter radiation, and the available laboratory measurements are simply not perfect enough to nail down the details at this composition. Another major limit involves the physics of convection, the turbulent, boiling-like motion inside stars. Convection is one of the most complex processes in astrophysics, and stellar models use simplified mixing-length theory to describe it. This theory works well enough for Sun-like stars, where the internal structure is close to what the theory assumes. But in metal-poor stars, convection's behaviour changes. The convective zones are shallower. Energy transport becomes more sensitive to low opacity layers, and the steep temperature gradients amplify the role of turbulent mixing. Adjusting the mixing length parameter can shift the age of Methuselah dramatically. Yet because mixing length theory isn't grounded in first principles, the parameter tuning is always approximate. A limitation that becomes painfully apparent when dealing with a star this old. Then comes the issue of nuclear reaction rates. These rates determine how quickly hydrogen is converted into helium in the core. Even tiny uncertainties in key reactions, for example, the proton-proton chain or the weak interactions controlling helium synthesis, modify the star's internal temperature and luminosity over billions of years. Most of these rates are measured experimentally in laboratories, but the conditions inside stellar cores differ from laboratory environments, especially at the extremely low metallicities Methuselah represents. Extrapolation is necessary, and extrapolation, when extended across nearly 14 billion years, compounds uncertainties in ways that no calibration can fully eliminate. Diffusion and gravitational settling add a fourth layer of difficulty. Heavy elements sink, helium sinks, hydrogen rises. The star's interior composition slowly stratifies itself, but the rates at which these processes occur and the extent to which they are counteracted by turbulence and rotation are still not fully understood. If the internal helium gradient is off, or if diffusion was more efficient than assumed, the age estimate changes again. For most stars, these changes barely matter. For Methuselah, they matter profoundly. Even temperature scales have limits on how accurate they can be. Models of star atmospheres are used to figure out spectroscopic temperature readings. These models assume certain opacities and convection treatments. If the weather model isn't quite right for stars that don't have a lot of metal, the temperature change that is inferred changes by thousands of Kelvin. Even though that small change may not seem like much, it moves Methuselah enough up or down the H-R grid to make a big difference in how old it is. This is why different tests have found temperatures that are only slightly different but give wildly different ages. The truth is that Methuselah exposes where the physics begins to crack. Stellar evolution codes are approximations stitched together from best-known equations, best-known laboratory data, and best-known numerical methods. They are incredibly robust across most of their parameter space, but they are not infinite in precision. Methuselah forces them into the region where assumptions begin to dominate outcomes, where uncertainties multiply instead of cancelling out. Yet this is exactly why Methuselah is so valuable. Every time a model fails to reconcile its age with cosmology, the failure points scientists toward the next improvement: new opacity calculations, new diffusion treatments, new helium constraints, new atmospheric calibrations. Methuselah isn't breaking stellar models, it's perfecting them. Lessons for the universe's first billion years. Methuselah does more than test models of stars or move astronomy forward. It gives us a look into the first billion years of the universe, a time we still don't fully understand. Events in this time period are so important and far away in time that not even the most modern telescopes can see them directly. The first stars came out. The first supernovae went off. Galaxies started to form from the bones of dark matter. The web of space took shape. The gap between galaxies changed from being dark to being bright with stars. And Methuselah was born in the middle of all this change. Its age alone tells us something profound. The first generation supernovae appeared astonishingly early, enriching gas clouds with the elements needed to form second generation stars, like Methuselah. If Methuselah is around 13 billion years old, then the universe's earliest star formation began when the cosmos was only a few 100 million years old. That fits with the emerging picture from JWST, a universe that produced bright, massive galaxies far earlier than expected, challenging assumptions about how quickly structure could assemble. Methuselah's age provides the stellar counterpart to that picture. Stars too formed early and vigorously. Its chemistry reveals even more. The high oxygen to iron ratio indicates that Methuselah formed in a region dominated by massive early stars, the first supernova factories. Those stars exploded quickly, sprinkling the early universe with alpha elements, but not yet iron. This matches predictions that population 3 stars were enormous, short-lived, and produced abundance patterns unlike anything seen in modern stellar populations. Methuselah is the smoking gun that these early supernovae were real, and that their chemical fingerprints survived inside second-generation stars. The lack of R-process heavy elements like europium tells us that neutron star mergers had not yet begun contributing significantly to the chemical inventory of the cosmos. This places an important constraint on how quickly compact binary systems form and merge, an important clue for gravitational wave astrophysics. It implies that R-process enrichment lagged behind the earlier star formation by hundreds of millions of years. Methuselah's orbit provides a map of the Milky Way's early structure. Its extreme plunging trajectory suggests it formed in a small proto-galaxy, one of many swallowed by the Milky Way during its violent youth. That means the Milky Way's halo the enormous spherical region of ancient stars and dark matter surrounding the disk, was built piece by piece from early dwarf galaxies. Methuselah is a surviving ember from one of those forgotten fragments. The star also offers insight into the early universe's thermodynamics. Metal-poor gas cools inefficiently, which means early star formation should have favoured massive stars. The presence of a low-mass star like Methuselah suggests that some small, dense pockets of gas were able to cool enough to form sun-like stars even at low metallicity. That tells us the earliest gas clouds were clumpier and denser than once assumed, capable of creating isolated low-mass stars that could survive billions of years. The story is also told in isolation. A little later, when gravity had time to gather gas into big star-forming environments, globular clusters, those dense old star swarms, came into being. Methuselah, on the other hand, seems to have formed before or outside of those groups. That suggests that the early universe was a mess, with star formation being random and reliant on the conditions where it happened. After many mergers, it wasn't until much later that the Milky Way started to form star groups and big structures that fit together well. Methuselah becomes a case study not just for stellar evolution, but for cosmological archaeology. It teaches us what star formation looked like before galaxies settled into disks, before dark matter halos reached equilibrium, before the chemical richness of later generations. It teaches us that the infancy of the universe was not quiet. It was a period of rapid, explosive enrichment and assembly. Methuselah also shows us how the world knows when to do things. It was created soon after the universe turned clear and is still alive and shining today. It covers almost the whole history of the universe. It was born when the universe was very young and has seen galaxies change over time. It saw the Milky Way come together and the Sun form long after the Sun itself was gone. It will live longer than many of the stars we see today. Why Methuselah survived when so many early stars didn't. If you want to understand how amazing Methuselah is, you have to picture the world not as it is now, but as it was a few 100 million years ago, when it was full of stars that are nothing like the ones we see now. The early universe was ruled by huge, violent, and short-lived giants. People in population 3 lived in these first stars. They got very hot, fell apart quickly, and died young. Everything that came after their blasts was changed by them, but almost none of them made it out alive. In fact, they were going to die. The early universe's physics almost made sure that the first stars had intense, short lives and didn't leave any straight children for us to study. And yet somehow, against that backdrop of stellar extinction, Methuselah, a quiet, low-mass, metal-poor subgiant, managed to live through everything the universe threw at it for nearly 13 billion years. That is not an accident. It is the result of a delicate combination of mass, chemistry, environment, and cosmic timing that almost never happens in the early universe. Methuselah is not just old, it is improbably old, a statistical miracle, a survivor from an era that erased almost all evidence of its own existence. The first reason Methuselah survived is its mass. High-mass stars explode quickly. Intermediate mass stars swell into unstable giants and shed their outer layers. Only stars with masses below about 0.9 solar masses can live long enough to survive the entire age of the universe. But those stars form less efficiently in low metallicity environments because metals help cool collapsing gas clouds. With fewer metals, early gas clouds tended to form only massive stars, not small ones. So the existence of Methuselah reveals something crucial. Some pockets of the early universe did manage to cool efficiently enough to form low-mass stars, even with primitive chemistry. That alone provides insight into early gas physics and the clumpiness of primordial clouds. The second reason for Methuselah's longevity is its stability. Many early stars formed in chaotic regions shaped by violent supernova feedback. In those regions, low-mass stars could be irradiated, stripped, or dynamically ejected before they ever stabilized. Methuselah, however, appears to have formed in a quieter environment, perhaps a small proto-galaxy or dense gas clump shielded from the most intense feedback. It survived the early chaos long enough to settle into a stable, evolutionary trajectory. But survival wasn't just about birth conditions. Methuselah also endured the Milky Way's violent assembly. Our galaxy grew by devouring smaller galaxies, a process known as hierarchical merging. This process created tidal shredding, shock heating, gravitational compression, and turbulent gas flows. Entire early galaxies were torn apart. Many of their stars were stripped from their homes and tossed into new orbits. Only the ones with enough internal stability, both structurally and dynamically, survived this frenzied era. Methuselah is one of those survivors, likely pulled from an early dwarf galaxy that the Milky Way absorbed long before its disk formed. Its current orbit, which goes deep into the halo, shows that it has been through gravity collisions that would have shook up less stable stars. That wasn't broken by the tide, it wasn't pushed into the center of the galaxy, where it could have been changed or killed by encounters with dense gas clouds or the early supermassive black hole. Its quiet makeup also suggests that it formed before surroundings became chemically complex. This means that after it formed, it didn't experience any internal pollution or mass transfer interactions that could have changed its evolutionary path. Another key factor in its survival is its chemical simplicity. Metal-poor stars like Methuselah radiate more efficiently and evolve more slowly because their energy transport mechanisms differ. This means they burn fuel at a slightly more moderate pace, extending their lives. Methuselah's low metallicity isn't just a clue to its age. It's part of the reason it's still around at all. But even after surviving the chaotic early universe, Methuselah had to survive billions of years of dynamical evolution inside the Milky Way. It had to endure disk crossings, tidal interactions, and gravitational perturbations. Halo stars like Methuselah have some of the most eccentric and wide-ranging orbits in the galaxy. These orbits expose them to constantly changing gravitational environments. Yet Methuselah's structure remained intact. There is no sign of external stripping, no chemical anomalies hinting at mass transfer from a companion, no evidence of past interaction with dense molecular clouds. It is remarkably unscathed. And then there is the simplest reason of all, probability. The early universe likely formed many low-mass stars, but only a tiny fraction survived. Most were torn apart, consumed by larger galaxies, altered by interactions, or disrupted by the mergers that shaped the early Milky Way. The handful that survive today are rare relics, fossils from the universe's dawn. Methuselah is part of this extremely selective population. The fact that we can observe one of these survivors so clearly is a stroke of cosmic luck. What Methuselah means for the future of cosmology. Methuselah is very old, but its importance in science is just starting to grow. Since it is one of the few stars that survived from the very beginning of the universe, it is in a place that is literally out of proportion to its small size. It is faint, small, and doesn't look like much, but it has huge consequences for cosmology, the evolution of stars, the formation of galaxies, nuclear physics, and even the current argument about how fast the universe is expanding. In the coming decades, Methuselah will continue shaping our models in several key ways. The first is cosmological anchoring. As long as Methuselah remains close to the universe's age limit, cosmologists must ensure that their interpretation of cosmic microwave background data, Hubble constant measurements, and early universe physics can accommodate stars like it. Even a slight tension will continue pushing cosmologists to refine models of dark energy, early expansion rates, baryon acoustic oscillations, and recombination physics. Methuselah doesn't challenge the Big Bang, but it tests its precision, and that role will only grow as measurements become more accurate. The second impact is on stellar physics. Every improvement in modelling Methuselah, whether through updated opacities, new diffusion treatments, better nuclear cross-sections, or more refined atmospheric modelling, filters into the broader stellar evolution framework used across astrophysics. Methuselah is not just a star, it is a benchmark. It will continue driving improvements that will refine age estimates for globular clusters, halo populations, and early dwarf galaxies. The next generation of models will be built with Methuselah in mind, ensuring that stellar physics performs reliably even at the edge of cosmic time. Third, Methuselah will help define the future of asteroseismology. If next-generation missions detect its oscillations or even constrain them, it will become the most valuable seismic target among ancient stars. That would open the door to seismic age calibrations for other metal-poor subgiants, establishing a new timeline for early star formation and validating or challenging cosmological ages. Methuselah will act as both a test case and a prototype for this frontier. Its fourth influence lies in galactic archaeology. As surveys like Gaia continue mapping halo stars, Methuselah's orbit and chemistry will anchor models of how the Milky Way assembled from smaller fragments. If future observations identify stars with similar chemical fingerprints, scientists could reconstruct Methuselah's birth galaxy, offering the first direct glimpse into one of the proto-galactic fragments that built the Milky Way. This would transform our understanding of early galaxy mergers. Fifth, Methuselah will continue influencing nucleosynthesis theories. The chemical composition inside the star holds clues about the yields of the earliest supernova, and as models of population 3 explosions improve, Methuselah will remain one of the key data points for verifying their predictions. Its unusual oxygen abundance, moderate carbon levels, and alpha element ratios will help calibrate the next generation of supernova models. And finally, Methuselah will shape the way astronomers think about ancient stars more broadly. For years, scientists assumed stars older than 13 billion years would be nearly impossible to measure precisely. Methuselah proved otherwise. It demonstrated that individual stars can compete with galaxy surveys and cosmic background measurements when determining the timeline of the universe. This shifted astrophysics toward a new appreciation for stellar chronometers, stars whose ages hold cosmological significance. In the years to come, Methuselah's impact will grow, not decrease. Its parallax, spectroscopic readings, seismic activity, and chemical makeup will all be improved by future trips. With each improvement, the gap between astronomy and star evolution gets smaller. Any change in how we figure out its age affects how we think about how stars formed in the beginning, the first galaxies, and when the universe began. Why Methuselah might not be alone. For many years, Methuselah was the only person in the world who really stood out, the one star who pushed the limits of time in the universe. But as telescopes get better, studies get bigger, and the halo is drawn in more detail than ever before. A new possibility is starting to show itself. Methuselah might not be the only one. It could just be the first member of a bigger group of very old survivors. And if that family does exist, it would have huge effects on astronomy, the development of stars, and the formation of galaxies in the early universe. The first clue that Methuselah might not be the lone elder comes from the growing population of extremely metal-poor stars being discovered in surveys like Sky Mapper, Lamost, Apogee, Gala H3, and Gaia DR3. Among these stars are several candidates whose metallicity and evolutionary state suggest ages close to the cosmic limit. Some are subgiants like Methuselah. Others are slightly evolved main-sequence stars whose lifetimes stretch nearly the length of the universe. A few possess even lower metallicities, bordering on relics from the second generation of stars, perhaps even closer in age to the first stellar nurseries. But these stars are much harder to age precisely than Methuselah. Many lack refined distances. Others have unusual chemical compositions that complicate modelling. Still others sit in evolutionary stages where small uncertainties explode into large age ranges. Methuselah, unusually cooperative in its subgiant phase, remains the benchmark. But these new stars whisper that the early universe produced more than one long-lived low-mass relic. HD 140-283 Methuselah is one of the best possibilities for a very old star like Methuselah. Other stars such as HD 1225-63, BD plus 17 degrees 3248, and the very metal-poor HE 1523-0901 also point to very old times. For instance, HE 1523-0901 was dated using radioactive decay chronometry, which compares thorium and uranium lines to stable elements to get an age of about 13.5 billion years. That puts it right next to Methuselah in terms of where it fits in the universe. These radioactively dated stars don't have the early older than the universe debate, but they all say the same thing. The process of stars forming early on was quick, violent, and very close to the speed of light. Then there are the carbon-enhanced metal-poor, CMP stars, relics whose chemistry indicates the influence of the earliest supernovae. Many CMP-no stars, those without neutron capture enrichment, appear to trace back to population 3 supernova yields. Some are so metal-poor that their birth gas clouds must have been enriched by a single progenitor, just as Methuselah's likely was. These stars aren't merely old, they capture the fingerprints of the first explosions. If even one of them enters the subgiant phase within observational reach, its age could rival Methuselah's. Recent JWST observations hint at something even more dramatic: early galaxies forming stars at breathtaking speeds only a few 100 million years after the Big Bang. If galaxies assembled faster and earlier than expected, then second-generation stars like Methuselah might be more common than previously believed. Stars formed in small, early collapse halos, quickly merged into the Milky Way's growing body, could be scattered across the halo today, hiding among the faintest and most metal-poor populations. But finding stars older than Methuselah, or even equally old, requires extraordinary precision. A star's metallicity must be measured with high-resolution spectroscopy. Its distance must be refined by Gaia or successor missions. Its temperature and surface gravity must be constrained through careful atmospheric modelling. And even then, uncertainties in helium content, diffusion, convection physics, and nuclear reaction rates must be accounted for. Methuselah is only oldest because the data allows it to be read more precisely than its peers. If those peers receive the same level of observational scrutiny, some might land in the same age bracket. The real breakthrough will come from future telescopes. Plato will provide seismic ages for metal-poor stars we cannot currently analyse. The Roman Space Telescope may identify faint, ultra-metal-poor halo stars in regions never surveyed before. 30-metre class ground telescopes, the ELT, TMT and GMT, will read chemical fingerprints deeper and clearer than any current instrument. As these tools come online, the number of candidate cosmic chronometer stars will expand dramatically, and when that happens, Methuselah will transform from an anomaly into a member of a population that defines the earliest timeline of star formation. Instead of relying on a single star to probe the universe's dawn, astronomers will use an ensemble of ancient relics. Patterns will emerge, ages will converge, and the uncertainties that once plagued Methuselah will shrink through cross-comparison. We might find a cosmic family tree with dozens of low-mass stars that are still around after a billion years. Each one comes from a different proto-galaxies that the Milky Way ate up. Some will have the marks of very large supernovae that happened very early on. Others will show areas of star development that are quieter. They will make a very clear map of the early Milky Way's chemical, structure, and formation. Methuselah might turn out to be the oldest member of this family, or simply the first one we recognized. Either outcome deepens the mystery because it means the early universe was capable of forming long-lived, low-mass stars much more efficiently than theory predicted. Nearly 14 billion years of cosmic history led to this one quiet ancient star. And if Methuselah has taught us anything, it's that even the faintest light can rewrite what we think we know about the universe. As astronomers keep sharpening the numbers and hunting for its long-lost siblings, the real story is only getting started. If you want to follow every twist in this cosmic mystery, from new Gaia releases to the search for even older stars, make sure you like the video, subscribe, and stick around for the next Deep Space Breakdown.